Hello. Okay. Hello. It's me again. I'm Mikerah, for those of you watching at home. And today I'll be presenting a merge mining sidechain scheme. But first I'll motivate the day, and then I'll show some scheme. So if you want to know about today's schedule, you could check this out. There's also a bit.ly link. So actually, I think the bit.ly link goes to the Medium page. I'm not sure if the Medium page has an updated schedule. Whoever's in charge of the website,
Oh shit. What am I supposed to do?
check if the schedule is updated. It is. Okay. Oh. Yeah. I made this slide a few days ago. So this is work co-written with John Adler. He's on the balcony floor, and he's wearing a Chainlink t-shirt. So if you want to talk about this stuff afterwards, you can come see me or John. And is this mic loud enough? Okay. So for a bit of motivation, we're all here this week to try and scale Ethereum. We're either trying to do so at the base level or at the L2 level. And yeah, the whole point of today is pretty much working without modifying the base layer. And the motivation for this work in particular was for the original goal, which is payments. So this doesn't really work for any sort of state transition. So too long didn't read. Short history of L2 scaling. Side chains kind of suck for scalability, so that's why they're used for interoperability. They make sense when you have a form of trustless peg, and for years we couldn't find a way to do that. So they're used for interoperability. So famously, Rootstock and Liquid use federated pegs, and then Namecoin uses merge mining. So instead of working on sidechains, payment channels were sort of the state of the art. And as you know, the Lineage network is still in beta after, 3 years, 2.5 years. So there's still a lot of work to be done. And newer approaches to L2 scaling, we have Plasma, which is an improvement to sidechains. And we have state channels, which you can do any arbitrary state transition in, and we have state channel networks. So there'll be other talks on Plasma and state channels during the day. So we've tentatively called our scaling scheme Ethereum Cash. If you have a better name, please give us a better name. Please, I hate this name. This is John's fault. So so we're presenting a sidechain scalability solution. It uses merge consensus, which is just a fancy way of saying it's not longest. It doesn't use a longest chain fortress rule. So it's not like basic merge mining, which has a bunch of issues. It has a two-way trustless peg. So now we can actually use the sidechain for scalability instead of just interoperability. It uses an UTXO data model, so it's much simpler to reason about, and it's more scalable than an accounts data model, and it doesn't make any fancy assumptions. In fact, it's no stronger than the assumptions in ETH 2.0. So James, who's here today, tweeted about this year, and it's sort of like, if you take anything from this talk, it's this tweet. Where he says, relay, a chain references a remote fortress rule. Merge consensus, a fortress rule references a remote chain. So the gist is, instead of the sidechain having to do a lot of the work, the miners on the main chain sort of do the work, but they don't really realize they're doing work for two chains. And that's quite powerful. In some future slides, we'll go into detail about how you can have like some interesting transaction fee markets. Also this slide as well. So take that tweet and this slide, like if you get anything from this talk, you're like solid. So if you're old enough and you like browse 4chan, you probably recognize this meme. So yeah, Jinx said to meme, so
What?
you said to meme yesterday.
Oh, yeah.
Yeah, so put memes in your talks, right? So like basic merge mining has a bunch of problems. First of all, since it reuses proofs from the from proof of work on the main chain, you gain no security because even though it's not susceptible to attacks from the outside, the miners who are mining can easily just attack the sidechain. You can have long hidden reorgs, and you have to create a new token and get paid in some new token. That's why nobody uses Namecoin. Whereas with merge consensus, really, you can still get paid in ETH. So this is like the new transaction fee market stuff that I was alluding to in the previous slide. And you make period commitments to the main chain, so it's kind of looks like Plasma, but it's not Plasma. We had this argument like on Telegram a few weeks ago. And in order to attack the sidechain, you need to attack Ethereum, which is expensive. So if you take anything away from the slide, it's this guy right here. So the white blocks are the main chain, so consider Ethereum. And then the red blocks are the canonical chain. And then the gray ones are the orphaned blocks. So say after like a long period of time, nobody challenges a payment, then we can say it's okay, it's been confirmed. Ooh. Yeah, and so there's a smart contract deployed, and in order to make this work, a bond needs to be deposited. So if it does get challenged, a bond can be slashed. So this slide has a lot of stuff on there. What should I talk about? I guess you guys can read it. Oh, by the way, I had a question about this. Does anybody agree with the statement Plasma Cash is channels?
Does anybody agree or disagree?
Agree. You disagree?
I disagree.
Okay. Told you so. Yeah, so I'll talk about that. So he was saying that in Plasma Cash, since whenever you deposit on chain, you create a NFT on the Plasma chain. This just looks like a channel on the main chain. It kind of seemed weird.
The 1 sentence answer is Plasma can add new users directly to the chain. You can't add new users directly to a channel.
They have to be fixed beforehand.
Yeah, you need an on-chain transaction to add a user.
What do you think?
It's a one to anyone channel. That's not.
That's not what a channel is.
I fucking love this presentation.
Channels proceed by unanimous consent. Plasma doesn't.
John, what's your response?
Tap lookup from both sides. Plasma doesn't. There. By direction.
John?
No response.
Yeah. Did you hear Jojo's? Can you repeat yourself?
Has collateral lookup requirements from both sides.
Can you repeat the things people say for the live stream?
Sure. So Huh?
you catch that? Georges said has collateral lockup requirements from both sides.
Plasma or channels? Yeah. So channels have non-collateral lookups from both sides.
Collateral lockups.
Collateral.
Lockups.
Oh, I was thinking custodial. Okay.
So like when you join a plasma chain, you can receive funds without having locked anything on the main chain. In a state channel, you can only receive funds that were specifically locked on the main chain.
Did you get that? What's your response?
I have no response.
Why not?
Because we're in a presentation.
Not really. I mean, like that. Oh, there's 5 minutes left, and like, let's be real. That.
Presentation is whatever you want to make.
Yeah, exactly. So now we're having an argument. So no response? No?
Mikerah, you try to be real spicy.
All right, another point. Channels can instant withdraw. Plasma can't.
Economic fast withdrawals.
Can you elaborate on the properties on the left side?
On which ones?
Ethereum Cash stuff.
Oh yeah, but which properties?
What's the incentive to Magmo launching?
John, this is your chance here.
The block producers are incentivized to validate other blocks. What if they don't? Then they might end up building on an invalid chain and get slashed.
Yeah, so I forgot to mention this, but there's a contract deployed on chain on Ethereum, and miners have to sort of interact with this contract as usual. And John is saying that a miner who builds upon invalid blocks gets slashed. So they're incentivized to mine on the canonical chain. Does that answer your question? John? No response. No. Okay, I guess you can talk to him afterwards. No more spiciness? Nope. Okay. Oh, Will.
Can you elaborate on the permissionless side? Just a little bit. Just a quick summary of why.
So miners don't need permission to do anything. In Plasma, there's like an operator, and that's permissioned. That's TLDR, really. There's a paper, by the way. I don't know if I linked to it. Maybe it's on the website.
We can link to it on the website. Great. Thank you.
Oh, Jeff.
I was gonna say, how would you compare the security model of Ethereum Cash to Drive Chain?
I never understood drive chains personally. John understands those. I've read the article like 2 or 3 times, and like, yeah, Truthcoin doesn't make sense to me. The guy who writes those articles.
Well, it has a similar tactic of kind of punting to the miners of the main chain.
Were you gonna say
I would
something?
say that you can in fact incorporate drive chain incentives in the kind of the absolute worst case. So the scheme here is basically no worse than drive chain.
Okay.
Eva, how much time? Okay, done. Oh, okay. You can talk to John afterwards.
Maybe that's not time, but if you could go back to the diagram, I didn't fully understand what was going on there with the mesh mining.
Is that 2 slides ago? Oh, it's this one?
Yeah, that one.
Oh, there's only 1 minute left though.
Yeah, it's fine.
Cool.
There wasn't enough spiciness in this talk.
There wasn't so initially. I didn't know you were gonna be so fucking spicy, but initially, this is a work in progress, and
Oh, right.
we wanted to encourage Mikerah to present to get feedback on the paper for peer review, and they've been showing it in the Plasma contributors chat. So, would you be down to send a link to the Telegram group? Yeah.
John, do it.
No, we're curious to do it. Oh my god.
This is my way of getting out of doing a presentation. Who's talking? Oh, Ben. Is Ben here? Oh, hi, Ben.
Woo! Plasma group. Wow. Plasma talk.
Yes, plasma talk.
I'm always spicy.
Oh my god.
Testing, 1, 2. Can y'all hear me? Can you hear me? Yes.
No.
No? How about now? Ooh. Are you just going to make me start until I keep yelling? That's what you're trying to get me to do. Okay. All right, hey everyone. I'm Ben. I work on an awesome team called Plasma Group. Jing, Carl, Kelvin, some really cool folks. And today I'm going to be here talking about plasma and where it lives in the design space. Okay. So if I were to pinpoint plasma most readily, I would say it was a small town in Poland. But that's probably not what we're looking for here. So what are we actually going to talk about? Okay, so I'm going to talk about 3 different scaling solutions. I'm going to talk about sidechain networks, I'm going to talk about channel networks, and I'm going to talk about plasma networks. And when I talk about them, I'm going to talk about 4 things. I want to talk about the scalability properties you get, the extensibility and usefulness of these systems, the security properties, and the economics. Okay, and what is a motivator for this? Well, I think there's no more badly used word in the crypto space than transactions per second. This tells you a very small subset of the information that goes into actually understanding what a blockchain transaction is and why it's valuable or not. So beware scalability metrics. We're going to try to go beyond TPS. Okay, so let's start. We'll start with channel networks. Hopefully you guys are all pretty familiar. You have Alice and Bob depositing into an escrow, and then they can make off-chain transactions, and then they can withdraw. So in terms of scaling properties, this is an example of where TPS is a little bit of a broken metric. I can send 1 Satoshi back and forth between myself in infinite number of times per second, but it's not really all that useful. What is a more useful metric to talk about is the fact that you require 1 on-chain transaction per participant update. So we were getting into this in the last discussion, but for things like adding or removing a person or changing their balance, that requires an on-chain transaction. In terms of usability, we do have a very extensible system here with state channels, amazing work by some of the people in this room and others on generalized state channels. So not only can we send money back and forth, but we can send chess moves back and forth and actually play out a chess game. It's not without caveats. So in general, it seems you can't do everything that you can do with a blockchain with a state channel network. Things like auctions seem are at the very least under-researched, and we don't understand how to build large participant set agreements. And again, you can't do off-chain onboarding of new private keys. Okay, let's talk about security. So the most obvious failure mode for a state channel is the malicious, your counterparty being malicious, a malicious participant. And the outcome of this is going to be that your money is locked up for a dispute period. And the likelihood of this seems high. Again, these are all systems that are evolving, and we'll see what happens in practice. But especially when we're talking about something like chess, if you blunder your queen on game 5, you're probably just going to rage quit and go buy groceries or something. And so it definitely seems like the case that we'll see state channel systems where people are going offline pretty often. Of course, there is a second failure mode, which makes things a lot worse if it's together with the first, which is a censoring main chain. And in that case, we can revert to an old state, which means that we can lose some safety properties if there's main chain censorship. If Phil is here, I would say fight me because I think that this is unlikely. And if we have long timeouts, there's reasonable economics at play there. Okay, and then the last thing about channels is capital lockup. So I can't stress this enough. The huge problem that we have with channels is the fact that for Alice to send a transaction to Carol, if they don't have a channel with Carol, they got to find some intermediaries who do. And the idea is that we have these intermediaries provide this as a service, but if we do that, then there's going to be a lot of money locked up in those hops, right? So this is a fun little lightning exercise that you can do with bead diagrams. So the question is, how many coins can Alice send to Frank? In one transaction is a bit of a misnomer, but in total, Alice can send 2 coins to Frank, right? So Alice has 9 coins in this system. The average number of coins each person in the system has is 6, but Alice can only send 2 to Frank. And so this seems not ideal. And of course, okay, so like full disclosure, I actually originally found this diagram on the Bitcoin Cash subreddit. So like it's obviously constructed and fake, and we don't know what these systems are going to look like in practice. But what we do know is that in economics, we should always be dealing with some background rate of interest. If money is locked up, there's going to be some opportunity cost of locking up that money where you could be going and doing something else with it. And so one thing that you can do to try to solve this problem is you can rebalance. So if you move some of Bob's coins into a different channel, then now Alice could be send more money to Frank. However, if you do that, that's an on-chain transaction, which means you have a choice in channels. You either have to have less on-chain transactions and less rebalancing, or you have to lock up more capital and have higher fees. So this doesn't seem ideal. Okay, so that's a bit on channels. Now let's talk about sidechains. How familiar are folks with sidechains in the room? I'm just curious. We got a good, nice. Okay. So that's great, but the rough idea is Alice deposits some money into like a peg, right, which sort of transmutes her money into pegged money on the sidechain. And she can send that to Bob, and then Bob can take it out of the peg at a later point in time. And like, you know, behind the scenes, we have a light client, like sort of contract running of some form. Sometimes we make the sidechain's consensus protocol like be that part built that a light client is super simple, but in general, it's kind of like a light client. And so these are the properties that we do. So in terms of extensibility, sidechains definitely win out, right? Because a sidechain is a blockchain, which is wonderful for doing things that blockchain people like to do. So it means you can have an unbounded participant set, all those wonderful properties. However, you cannot talk to other chains without this pegging mechanism. So you need on-chain transactions on both of those chains to be able to, perhaps both, to be able to communicate between the two of them. And so you get you have unlimited participants in terms of like public keys interacting with your sidechain, but it's not unlimited interactions with other parts of the network, other blockchains in this sidechain network. In terms of scalability, again, it's hard to answer for this because it's like there's a lot of different blockchain consensus protocols, and they have a lot of different throughputs, and so the scalability depends. But again, one thing we do know is you're going to have one transaction per peg or like IBC action. And again, like we're all familiar with the world of blockchain scaling, it's almost as if you're shifting the scalability problems to a sidechain, but you still have to put a consensus engine that scales things together, which is hard. Okay, and have I mentioned it's a blockchain yet? Right, so economics. So again, the economics securing a sidechain system are dependent on the economics of that sidechain, right? So I'm gonna, there's no way to cover all of that, and that's still ongoing research into how, proof of stake and all that. But I'm gonna just give a rough, dumb heuristic anyway. Okay, so let's imagine we have one chain, and let's call that chain as having some amount of validated, some security. Let's call that one security unit, okay? Now let's say we want to scale by taking this one chain and taking all the resources there and turning it into 2 chains. So then we're going to have a half of a security unit at all of these things. So maybe it's not linear. That could be the case. But this is a rough heuristic for what's happening, right? And actually dividing your security in half. Because the problem with pegs is that they're weakest link. So if you issue an asset on one chain and via a peg transmute that into another chain, someone using it on that other chain is at risk of either consensus mechanism failing to lose their money because the original token supply is here and what they're doing with it is here. And so what this means is that not only have you split the sidechain, not only have you split the security in half, but you've also made both of those halves vulnerable to breaking your system. So you've intertwined weakest link security. And the failure mode is, of course, all the money is stolen. How likely is this? Again, it depends. It's a blockchain, but it seems as if by dividing the security, we're making it more likely. So I would say the TLDR of all that is that sidechains still are very useful, but what you're going to get, and what you do get when you divide these 2 chains, is you're going to get lower fees and more scalability. But the trade-off that you make for that is you get less security. And that's great. Not everything needs the security of the Bitcoin blockchain. Okay. So the last thing that I'm going to talk about is plasma networks. So can I get a sense of familiarity on plasma? Oh, okay. I like that. All right. We got a lot of plasma people here. That's amazing. Okay. So yeah, again, just to give a rough idea, it looks kind of like a sidechain, except we're committing every block header to the main chain, and we use an exit game in place of this light client, where the exit game sort of acts as almost like a cryptoeconomic light client that's also doing some verification. Right. So that's what we get. Okay, let's talk about the scalability of Plasma. So in Plasma, you have one transaction per deposit, one per exit, similar to channel, similar to a sidechain. You also have a constant size commitment per block. So what this really means is that if you were using only one transaction per block, you're actually not getting a lot of scalability with Plasma because you're just like hashing a transaction and shoving it in, and you're paying a pretty good amount of gas for that. When Plasma is really useful is when you can take a large number of transactions and amortize the cost of this one 32-byte commitment over many, many, many transactions. So you want to be alongside people. So it is a constant size commitment for block that is linear. There are some skychain schemes, and certainly channels don't require like any updates to the main chain. So that's definitely a difference. Okay, in terms of failure modes, there are two failure modes. The sort of Plasma-specific failure mode is second, it's an invalid block. So there's this, in Plasma, you have this party that is committing these hashes. It's like an aggregator. They're just taking a large number of state updates, aggregating them, plopping them on chain. They can't do anything to screw you over in terms of stealing your money, but they can do things to lock up your money, because the way that you fall back from an invalid block is you wait a dispute period and prove that the thing was invalid, and that requires waiting time. So what this means is that in the security failure of an invalid block, you'll have time locked up. What is the probability of this? Well, again, just like channels, we're not sure what these things are going to do in practice. Our intuition is that it's going to be medium probability, if not low. And the reason for this is, unlike rage quitting a chess game, the person doing these aggregations is really only there to be making fees. And so the only thing they stand to do by producing an invalid block, since they can't make money, is to lose out on the net present value of like all future fees that they're going to get discounted to the present day. So it seems like they're not going to want to do that, because why would you? And then lastly, if you have a censoring main chain similar to payment channels, you can, and this is different from channels, all the money can be stolen. Yes, question? Where do data availability, okay, so great question. So the question was, where do data availability risks fall in all this? So the beauty of Plasma is that it is fully safe under a lack of data availability. So when I say an invalid block here, I'm kind of hand-waving an invalid block that is withheld, and then another invalid block that is withheld, and so on. And so the property of Plasma is, because you can pull out from previous old available states and exit that, then the unavailability of things in the future does not matter. So the way that we think about it,
Depends on Plasma flavor.
Generally depends on the Plasma flavor. In the more vanilla flavors, we'll say that that's how it works. And in general, this is the intuition that we've had, is like things like ETH2 are trying to make a lot of data available. Plasma is trying to make a lot of data not required to be available to have security in the system and be able to progress the state. Yeah. Okay, so just to touch on economics for a minute. You do not have capital lockup for any participant in this system. So there are no intermediaries for Alice to send to any private key, including like a newborn baby, right? We have this issue that you can't make as many lightning transactions lightning channels per second as there are like people being born. You can create as many entries in a Plasma block as people exist, probably, I think, if you have a big enough computer. And you don't need to lock up capital to move money in between all those people. So that's a wonderful property of the economics. We do have a pessimistic failure, which is time lockup. That if an invalid block or an invalid or withheld block occurs, then we do have money that's going to be locked up. So it's unlike channels, where in the happy case, everyone can immediately withdraw their money because the chess game was over and we want to use that for something else. In Plasma, that's not the case. You can't get your money out. This is actually literally, though, only in the case in which the aggregator, the person generating these blocks, is malicious. If they're not, then we think that in economic equilibrium, the UX of these things will not have any withdrawal or deposit times associated with them, which is pretty neat. How am I doing on time, by the way? Time? Oh, I have 10 minutes. Ooh, we have time for some questions. Okay, so the last thing, okay, well, as I say that, it's time for me to shill some of my own stuff. So Plasma Group has been spending a lot of time working on what we're calling generalized Plasma. And so for the first time, we think that we have a truly extensible architecture that gives you a way to build Plasma that can be expanded, which is really, really sweet. So what can you do with this? Well, first of all, you can build Plaps, which is just the most amazing meme ever. And there's a fair number of things PLAPs that you can build. So one PLAP you can build is a state channel. So this is like obviously like a match made in heaven. Imagine all those problems with paying on-chain fees for rebalancing and moving them off-chain. Seems pretty juicy. So channels are a really big one. You can also do things like decentralized exchange. Like atomic swaps at the plasma layer are much nicer than atomic swaps at other layers. Similar to state channels, I suppose. You can also do like futures and options contracts. And we think more. Really, the only property that it requires is that you have some way to resolve disputes in a succinct manner. So like if you write an arbitrary state transition and you can't come up with a way to like argue about what the right state of that is meaningfully, then the only way to figure it out is to play it all back. But if you play it all back, you lose the scalability. So it's unclear what the limits of Plasma are going to be, where we're going to get to the point where there is no succinct way other than just running the code to know what the right Plasma state is in the event of a dispute and when it's not. But we have hope that there's going to be a lot, and it seems like there will be. Okay, another really cool one, and this is one that has really only come up to us very, very recently in like the research process, has been, you'll notice that I started this with plasma networks. Plasma network is like networking plasma chains has not really been something that's been on the radar in the history of Plasma, and it's now on our radar a lot. So basically, the intuition is as follows, and this came out of our research towards generalized Plasma. We were trying to build contracts which were agnostic to the Plasma chain. So we needed to build like a contract that represented your notion of ownership, so who owns what, and saying that Alice owns this thing. And you wanted to be able to reuse that between Plasma chains. And what we realized when we did that was that all these Plasma chains share something in common, and that is that they do disputes on the main chain. And so not only are there disputes all happening in the same place, right, and all that money is locked up in the same place, but all the main chain has access to all the other main chain. It's all public variables. And so what we finally realized is that unlike something like a side chain in which you require this IBC to connect the two together, all Plasma chains are fundamentally linked because their exit games can look at each other. So every single Plasma chain that is within the security parameters that you care about is really like it is your Plasma chain, right? So this is an incredible property that we hadn't realized. So doing an exchange, an atomic swap, a trade within a Plasma chain and between two disparate Plasma chains, as long as they have the same timeout that you care about, is exactly the same. And we had no idea that this was the case until we started building this generalized system. So that's a really big deal because it means that effectively you can think of all of the Plasma states on like Ethereum as really just being one big state. And it's really like what we've done is we have sharded them. So I'm pleased to announce plarding. No, just kidding.
Wait, can you go one step back so I can take a photo?
Okay, no. Okay, so I guess we're able to wrap up in time here for questions, but I would just say, like in conclusion, like the way that I think about the trade-offs in layer 2 are that sidechains are really good when you want to do complex things that you can do with blockchains, but you can't figure out how to do in terms of disputes, and you're okay with having lower security. And then channels are really, really good at having instant finality and all these wonderful properties, but capital lockup seems to throw a real wrench in things, and it's the perfect marriage with channels. So in the long term, like Plasma rather, yes. Channels are also a great match, but not as good as channels and Plasma. So it seems like in the long term, what we'd really love to see is that we have lots and lots of Plasma constructions being used where Plasma can be used. And one of the central things it's used for is channels. Because if you rebalance off-chain, then you can frequently rebalance everyone's money and not have the on-chain hit in scalability that you were taking before. So that's about it. I'm happy to answer questions about any of this as well. Yes, Alex got his hand up.
Explain a little bit more how the interoperability will work. Like if I make a transfer from one Plasma chain to another.
Sure.
You need to make atomic blocks or like.
Sure. So you don't need to make atomic blocks. Every one of these Plasma chains we assume has a different aggregator, putting transactions with a different public key at different times. And basically, the property is as follows. So this is all related, like I said, to the generalized Plasma stuff. So in generalized Plasma, you write these external contracts called predicate contracts. And these predicate contracts really define all the details of Plasma. Plasma can't be used without at least one predicate contract. For instance, the notion of ownership itself, saying that Alice owns this, requires that you write some form of ownership predicate. And you can actually design a few different ones. So it does require that you build a atomic swap predicate or a trade predicate. And you need to define some parameters about what happens in the case of those disputes. And there's a few different ways that you can structure it. But the short end of it is that as long as you structure it so that the atomic swap blocks can be two like different things that didn't happen at exactly the same time, just to make sure it's safe in that condition, then it's just the fact that you're going to Ethereum and reading the state of like these inclusion proofs, and all of that information is public. So like I'd be happy to go in maybe off after this about like the details of that, but the intuition is just that because all the data is in the same place and because it all accomplishes the same thing, then like it's really just that easy. It's just plug and play. Yeah. Jeff, did you have a question?
I was going to say, true or false, this presentation is entirely to refute the earlier claim that Plasma is channels.
False. Okay. Oh, yes. What up?
Curious, is there like an estimate for the first plot to be implemented?
The first plop is done. It's called ownership. Yeah, so I mean, like the notion of like what you can build on plaps is definitely a very interesting question, and like whenever we have like spare time to do research, that's definitely one of the things we love to think about. And similar to channels, the boundaries of what you can push with plaps seem to be limited in some way. We think less than channels, but are definitely probably limited. Because of the fact that you have to resolve things on chain. But we can do, for instance, like a crowdfunding campaign where you put up a bunch of money, and if it doesn't exceed some threshold donated, everyone gets their money back, and if it does, the money goes away. But there's lots of weird things to consider. For example, if you do that, you have to be able to handle disputes about that. Writing a predicate is writing about something in a language of disputes. And so what this means is that to do a crowdfunding contract, the only way to dispute that money was indeed filled up, like the crowdfunding goal was reached, is to prove with an exit that that crowdfunding money was reached. And so this basically means that like the more complex a dispute around something is going to be, like the more dangerous it is in terms of like what the on-chain gas cost is going to be. But we think that you can do a lot, and like crowdfunding is reasonable within that that frame. Yeah.
So between like if you're one in top right, I presume you're then combining two predicates, right, from different chains with constructions. How do I know that the predicate from chain A, right, is actually secure? Secure as mine, and I'm not buying in, quote unquote, buying into
Right.
into a trap.
Right. So the question was, how do we know that predicates are safe? Well, we definitely don't. There are definitely unsafe predicates. So that's totally right. And the way that you have to write, like, the predicate like development process looks like building the contract, building the client and operator, the client and aggregator like plugin system that works with that new predicate. Deploying the contract to the main chain, and then pushing out an update that adds this to a whitelist of trusted predicates. Because if it's just some random thing, for instance, if you set the 0 address as the predicate, it interestingly doesn't do anything. It actually, you can just continue on doing it. It doesn't burn the money because of like weird details of how the function calls work. But if you send it to like a contract that has one function but not another, the money can be locked forever, or things like this. So you definitely have to like prepare for a predicate to be safe, and then upgrade your client to like add that to the whitelist. Absolutely, absolutely. Yep, Alex.
So it's often the case that when you take two secure things and compose them together, you get something insecure. I know this is just five, but if these plasma chains all have different semantics, it's hard for me to imagine how you can be sure that you can compose two chains and get something with.
Okay, yeah, so the question basically was often in case if you put two secure things together that produces an insecure thing, how can you be sure that Plasma does this and like it's not insecure in some way? So maybe one like additional thing that would help clarify this is you do have to assume a trusted source of like Plasma contracts. So you would create like a factory on the main chain that like spits out Plasma contracts that you know are authenticated, and the Plasma chains would only allow trades within those authenticated sets. Does that help?
So it's not that you can compose plasma chains with get something reasonable. Is that right?
Yeah. So definitely you have to do like a lot of reasoning on a bespoke basis right now, especially right now where the developer tooling like doesn't really exist. You do have to spend a lot of time reasoning about whether is this system safe. Basically, the way to think about it is predicates, like smart contracts are written in the language of state transitions when transactions apply these state transitions. Predicate contracts are written in the language of disputes. So they resolve what the state should be once a dispute occurs. And so this is a different way of thinking about it. And you definitely have to think about whether or not disputes are going to work and be safe for this particular predicate. Yes, I'm going to let.
Really quick,
Okay.
one sentence. Would it be correct to say that just like you have to whitelist predicates, you have to whitelist predicate compositions?
You do have to whitelist predicate compositions. But doing a cross-plasma chain trade is not predicate composition. It's simply using the same predicate on two different plasma chains and the glory that comes with that.
So, I mean, while we're fudding about universal composability here, I just wonder what's the status of like formal security proofs of even a single plasma chain?
It's a great question, and we like need more of this. I think it's been tough because generally the plasma space has been in flux a lot. So this was one of our favorite things about the predicate model was that it actually removed a lot of complexity from our code. It made things simpler. And we have this core little nugget that we can call plasma and be more confident that it's plasma and like feel good about getting that, like audited and proven. So I think we're closer now more than ever, but the process is still far from complete. Yeah, definitely. Okay, I think we're good on time. So thanks everyone.
Coffee. Our next speaker is Skyping in, so y'all have a hot second to go get your caffeine.
I like coffee first.
Hi everyone. I'm not sure if you can. Hello. Can you hear me? Okay. Great. So basically, Eva is on Telegram and pinging me if you can't hear. So yeah. So I can't hear you. So if you can't hear me, just tell Eva to ping me. So it would be better for us to communicate. Sorry, I had to come on over our Hangout because I couldn't get my visa on time. So yeah. So my name is Jaynti Kanani, and I'm a co-founder and CEO of Matic Network. So we have been working quite a long time on Plasma Mode VP particularly, and we so currently current Plasma landscape is not the same as we like to think over it. I mean, there are multiple usability problem right now on Plasma landscapes, right? And we are working on some of those to address some of those problems. I'm going to talk about those problems and how we can solve those problems along the way. So it's a Plasma, and I'm going to talk about like partial confirmation, keys, and bonds overall in Plasma. So at Matic, actually, what we do is currently we are building account-based MoVP Plasma. So we are actually using log receipt instead of just UTXO like other Plasma models and Plasma cache. So currently we have testnet ready like for Plasma security assets for ERC like ERC20 and ERC721 transfers, and also we are looking into the predicates and how we can leverage for general state Plasma. So yeah, we also use proof of stake consensus for our sidechain to make sure the chain goes on, and it actually reduces the overall data where validators actually put stake on the main chain, Ethereum chain, and the contract, and then start validating and pushing the Plasma commitments on the Plasma root contract on the main chain. Of course, we actually also want to we are tinkering with state exit from Plasma to main chain, but I mean it's up to like predicates how we can design it, and we can actually move our state from sidechain to main chain. Currently, like we only do like ERC20 and ERC21 balances, but in the future we want to do like DEX, also like marketplace, other contracts and state. So yeah, so main focus here is like on usability, and so yeah, so we so what so first of all, what kind of how we actually achieved accounts in Plasma. So what we are currently using EVM only. So what we are doing is like we are using log receipt, where we have like token form2 and a balance and input like UTXO kind of model on accounts like input 1, input 2, output 1, output 2. It's a simple like sender receiver output and inputs on the each transfers basically. On when you exit, we actually need to provide a more like huge state and proof of inclusions also on when you exit from the Plasma to main chain. So the problem using EVM and accounts is like you have like a larger size for state for exits basically. So if you see here, you can actually see like in this code, like we have like three kind of different transactions and proof of inclusion here. So the basically size and gas fees when you exit is like a little bit higher instead of like other plasma implementation, but we are actually met the trade-off to make sure our usability on the sidechain remains like good instead of like when you exit. Yeah. So yeah. So currently this is like normal Plasma. If you see here, like we have like multiple Plasma blocks. It actually pushes the commitment on the Ethereum contracts, Ethereum Plasma root contracts basically. The problem here is that you can't push multiple blocks of Plasmas on the Ethereum chain. Like let's say if if the size of current block time of Ethereum block is like 14 seconds, you can't, your plasma block time can't be less than that. So it's exactly Ben Jones presented last talk. He said it's not about TPS, it's about how much transactions you put on one block and pushes the third commitment on the Ethereum chain. But what we can do is we can actually have like partial confirmation on each plasma transactions. So what we can do is like we can actually have like multiple like let's say 1 or 5 seconds blocks of plasma, and operator can just sign on those plasma blocks, or you can say signs on transactions on each transactions, and broadcast to the users directly. And once after let's say thousands or let's say 1,000 plasma blocks completed, it pushes the hash of the plasma blocks on the Ethereum contract as commitments, right? So basically what we can achieve by doing that is that we have like partial confirmation of 1 second or 5 seconds, and we have like finality of like let's say Ethereum block time is like 14 seconds, so we can have like a 1 minute or 2 minutes of finality over transaction. So let's say if you want to buy coffee on Starbucks, as you said, right, you can do that like with say, hey, this is the signature from the operator. He will include my transactions in the next checkmate commitment. So I'm actually secure that my transaction will included in next commitment. Basically, this is kind of you can also say it in fast finality, as Omisego said once. But this is like you create small blocks, small size block, like 1 second block, and then you can push the hash of all the root all the blocks on the commitment in the plasma. Right. The problem with this approach is like operator can sign like 2 partial blocks at the same height, but what you can do is like you can have like challenge on the main chain saying, hey, you already signed 1 block on the main chain, so the operator amount gets slashed basically. So in that case, you also need to have like operator has to put like huge bond on the main chain. But since we are actually using proof of stake, so every validator will have some kind of stake on the main chain, and if they sign like multiple blocks on the same height, you can share them easily if you have signature of any validator on with you, right? Of course, your large proof size will exit when you exit from the sidechain, because now you actually have 2 Merkle root, right? So one is for like simple transactions in the block. Now you have also proof for you have like block in one commitment, right? So first we have like 1 block with 1 commitment. Now we have like multiple partial blocks in each commitments, right? So in that case, you need to have like larger proof size for your what exit basically. Yeah. So now landscape, so most of the plasma in the main chain on testnet, people actually don't actually taking the fees right now, because the problem is that different flavors of plasma have kind of different fees problems, right? If you think about the plasma cash, it's NFT, right? So you can't just do like fungible fees on plasma cash. If you take more VP or more MVP, you need to have like multiple UTX on each transactions to operator, right? So operator will have like huge amount of UTXO as a fees, right? In plasma cash flow, you need to have like smaller ranges for operators, right? So I don't know. So there is a problem of defragmentation in cash flow. So if you have like multiple small range over huge, on a huge surface, you need to defragment over time. So that's a problem on any kind of plasma. If you look at it, the fees are we put a factor of the plasma, but there are some problems on current model. Plus also, so basically we have talked about many dApp developers and many dApp users. They actually want like different kind of fees model. Like let's say someone said, hey, I want to pay fees for my users. Some developer says, hey, I want to pay fees for my developers, for my users. Some says, hey, if I pay like $1, I can have like next 100 transactions free kind of stuff. So I don't know, I can pay in different tokens basically. So those fees models people want in Plasma when it scale the dApps. So what we can do is that we can use multiple things to extract the fees out of Plasma. So what we were been thinking about, we can use like 100% meta transactions. What it is mean by meta transactions? So think about the Bitcoin transactions or Ethereum transactions right now, right? What you can do is like you pay directly to the miner. Let's say hey, this is the $10 cash. Just take it and just include 100 transactions from my address into the Ethereum for free for me, right? Whenever, let's say, I give the miner like $10, they will include next 100 transactions with its gas price 0, because we had an agreement before my transactions, right? So what it means that you actually not paying fees on the while making transaction, but you can actually extracting away from your layer of Plasma, right? But the problem is that how you can maintain those contracts offsite of chain to miners or maybe validators or maybe the operator, right? What you can do is that you can use payment channels, right? What you can do is like you can create a payment channels on the main chain with operator for fees, basically, right? What it means is that you just have like when you deposit your tokens on the Plasma root contract, you also create a simple payment channel with operator kind of stuff, and you just have like, hey, I'm gonna pay maybe probabilistic payments if you have like multiple validators, or maybe just simple payment over set channels for including your transactions on the Plasma chain, right? So yeah, what here, so simple is like Alice is making a Plasma transaction so they can actually communicate with the operator with the signature of the transactions. And if something happens bad, LS can go to the Plasma root contract and start a dispute, and operator just say, hey, I actually provided your transaction in this block. This is the proof of inclusion. And both sides can operate like resolve the dispute on the main chain without any problem. Right. So yeah, last thing I'm gonna talk about is selective bonds. Selective bonds basically. I'm not sure if you know when you exit or do like dispute on the Plasma from the Plasma, you need to put a bond on the main chain. Right, a big bond is very important, because let's say if you don't put a bond, you can actually provide it increases the risk for like fake challenges on the Plasma when you exit, right? So the problem with the problem with the bonds is like normal user don't want to like put a bond when they exit. So let's say it's like paying putting a bond or deposit on the bank when you withdraw from the bank. Similar situation, right? So what we thought about it, that how we can actually put like zero bond when you make a transaction on the sidechain or on the Plasma in a happy case, right? So let's say if I have 10 tokens on the sidechain on the Plasma, how we can actually exit with 10 tokens from Plasma to the main chain without putting a bond on the main chain, right? What one solution is to have like kind of definitive exit from Plasma. What you can do is like you can actually transfer your tokens to address 0 or some address on the sidechain on Plasma, and when you exit on the main root contract, you can provide those like burn proof on the main chain, and everything works exactly as a Plasma priority queue, etc. And something goes wrong, you can always slash the operator bond, saying, okay, hey, I already bond my tokens on the sidechain, and you need to provide like, so let's say if operator cheats here, and it allows a user to make a transaction, even if you made a definitive exit, you can actually challenge or maybe start exit from your Plasma in that case. So here, actually, what you're doing is that you are actually making a happy case. Let's say everything works exactly as expected. operator is honest guy. You make a transaction on the plasma and you make a definitive exit from the plasma to main chain. You don't need to make a bond when you make an exit on the root contract on the main chain, right? So yeah, I mean, this is small things we have been working on Plasma and how we can make a user experience much better over time. Currently, we are working on most of the other stuff like so the problem with NFTs on the Plasma is that you need to transfer all the NFTs in like you can do like in loop, but you need to make sure you actually do all the transactions to move your NFTs on the Plasma. So what we can do also is that we can mint NFTs on the directly on Plasma, and when you exit you can actually mint on the main chain, right? So for that you still have some limitations over it. So let's say if you mint your NFTs on the Plasma, and then you need to wait for next commitment, you can't actually transfer before your next commitment. If you wait for the next commitment, then what happens, like we actually consider that minting as deposit on the main contract in the Plasma. So if you have like this kind of structure, you can actually consider this kind of like minting on the Plasma with very safe Plasma exits. Also, we also looking at the predicates as Ben mentioned on earlier talks. So what we are doing is like we currently have like ERC-2721 kind of predicates design. So if we have like same predicates and same exit mechanism for all Plasma, we can actually have like multiple we can have like interoperability between multiple Plasma chains, and you can move your state from one to other using Plasma interoperability. We also use exit NFT. So basically, currently, like it takes like 7 days to you can have when you exit, your exit will become kind of NFT. I mean, you can use the different kind of EIP or different kind of structure, contract interfaces, but we use the NFT because we want to actually leverage the decentralized exchanges right now, like 0x or other DDX or other marketplaces exist today on the main chain. So what we do is like we create like NFT out of exit, and you can sell your NFTs, and when 7 days complete, your NFT gets spun, and the owner will get the tokens back. In that case, so the exitor will have like thinking to use state channels on Plasma on the and main chain to move asset from Plasma. So we actually talking with the Connects team and see how we can use leverage of Plasma state channels from move our asset from Plasma to main chain using payment channels specifically. Yeah, and last point I want to talk about is so we actually use proof of stake mechanism to push the commitment on the main chain. What we can do is like currently we are actually looping through all the signatures on the contract and saying okay 2 by 3 plus 1 validators has signed the commitment or not. What we are actually looking into is like we can use BLS signatures to do a simple commitment on the main chain, and BL signatures verification can just do a simple 2 by 3 plus verification, threshold verification, and we can good to go. Yeah. So yeah, I mean that's it from my side. Thank you all of you. I can't hear you, so maybe Eva.
You don't have a question, Nice. At least we got a photo for Twitter.
Oh, that's Lucas. Lucas or
mass exit problem. So we are actually taking a look at crypto cash flow and how we can leverage it to on our model on Ethereum. And so yeah, the problem remains the same, like fees. So we are also taking a shot at fees, how we can solve together on Matic. Yeah.
How has your experience with predicates been so far?
So basically, the next question is how has your experience with predicates been so far? So we are actually using two predicates, and we are actually thinking how we can move our. So let's say I'm currently using one predicate, and I want to swap my tokens atomic swap on the plasma using predicates like two predicates. How I can assure that like one predicate is like secure, another is like secure in such a way when the atomic swap is like the whole secure. So I guess Ben Jones answered like in last slide that we have to white list those predicates. So maybe we can look into that in those directions. So currently, like the overall predicates experience has is better. It's good so far. So it's a pluggable, so it like looks like it will work with our model also. Yeah. The next question is, does the Matic implementation complement other Plasma chain designs? Yes. So basically, I'm not sure if the most people know about the Plasma calls, but we discuss how we can leverage each other's design in Plasma. So what we can leverage is like the predicate parts from the cash flow, right? So that's the one thing. So, and we also looking into the interoperative between multiple plasma chains. So let's say the plasma group has like one plasma chain and Matic has one. We can just do like transfer between tokens from one chain to other chain. So yeah, definitely. Thank you all of you. Thank you. Thanks, Eva.
So there's a keyboard here. And just use this.
So, hello everyone. My name is okay. My name is Yuriko Nishijima. I'm here from Crypto Economics Lab. Today, I'm going to be talking about some of the key features of our cash flow flavored plasma implementation, and it's called Plasma Chamber. And I'll share some of the updates of our recent plasma R&D, focusing mainly on predicate design patterns. So, at AtGon, which happened in Sydney this April, we played a demo of our transfer dApp built with Plasma Chamber so that we can convince everyone that how an application built Plasma would be useful in a real-world situation. We filmed this video acting as if we are buying a coffee with this really fast and scalable transfer dApp with DAI stablecoin. We upload this video on YouTube, so you can go watch it if you're interested. And what you can do with Plasma is so much. But the fact that the TPS will improve, although Ben was just saying TPS is such a vague concept, I totally understand that. And also too, it allows users to use dApps with less gas cost, since the operator can pay for them. And also, these are pretty much common qualities of Plasma, but in addition, the dApp built on top of Plasma Chamber will be able to work on mobile with instantaneous finality. And also this app was we built this app with fast finality function with the stablecoin. So, and this is the UI, how the UI of the application look like, and those are the links to the application used by the customer, which was me in the video, and coffee shop owner, with the shop dashboard. So you can please, if you're interested, please visit and play with them. It might not be working properly if the testnet version is updated, but you can look how it is. And so before deep diving into our research, I like to be on the same page with everyone. So this is what we define Plasma as. We define Plasma a transaction compression mechanism without sacrificing main chain security. So, but it has been not that useful so far. So there have been tons of things that needs to be brushed up from a usability perspective. So on ETH research, there's been a lot of discussions and proposals made by those Plasma researchers, but can each dApp project hire these genius Plasma researchers and form a protocol R&D team to just build one application? And it's going to be quite difficult. So that's why we wanted to build this framework called Plasma Chamber, so that dApp developers can easily and individually build secure and actually usable dApps on top of Plasma. So what I mean by cash flow based is it employs some Merkle tree and to avoid mass exit for the security guarantee, and it can merge and split ranges to treat NFT fungible by defining start and end point here. So let me dive right into the specs, starting off by our fundamental security model. So this is our exit game, and simple. We call our exit game simple because it's non-interactive. With Plasma Cash exit game, there was this possibility that rearrangement attacks happens with invalid history challenge. And in this case, Bob is an honest user trying to exit, but there is a possibility where operator is malicious and come right in the middle of Alice and Bob, pretending Alice money is supposed to be sent to operator but double spent by Bob later. In this case, Bob's transaction can be challenged by an operator and Bob's exit will fail. So to solve this edge case, we learn transaction is Alice, so he gets the first priority instead. So this proposal is posted as another simple exit game, blah blah blah, on ETH Research by Shuhei, our lead engineer. So please go check it if you are interested. And next is defragmentation feature for gas ghost reduction. With Plasma Cache design, the process of assigning unique IDs to each segment's range of UTXOs allows users to optimize the proof size that they have to hold on their wallets. However, another problem, fragmentation of index segments, arose here. Since each fragmented segment of the coins requires the same amount of gas ghost to exit, the more fragmented segments each user holds, the more gas ghost will be required for them to exit. As a result, fragmentation is very inefficient from the perspective of the transfer recipient. So they might have to pay a ridiculous amount of gas ghost compared to the fund he's withdrawing. By implementing the fragmentation feature, Chamber allows these segments to get merged by atomic swaps and reduce exit cost, allowing micropayments on Plasma, like the line in the bottom. And next is checkpointing for proof size reduction. Plasma checkpointer is implemented to reduce coin history data size that each user has to hold on their wallet. By creating checkpoint where everyone temporarily agrees that all the commits to root chain before that checkpoint are finalized with regular interval, the linearly growing transaction proof size can be reduced to some small constant. You might think, how is it even possible to trust all the commits by an operator without verifying them? Without getting everyone's consensus. To answer the question, challenge period is needed to contest the current state. If no one shows that the state is invalid during the period, then the checkpoint is finalized. In our implementation, checkpoint period is set 3 times longer than the exit period. So with these periods, the history data size on each wallet will be reduced. So, yeah. And the last feature that I'm introducing is fast finality. So normally it takes around 2 to 7 minutes to get root chain finality, combining child chain block time and root chain block confirmation. So far TPS is improved by Plasma, but time to finality has not. But with fast finality function, we aim to provide finality on Plasma chain within 2 seconds, and with security guarantee of collateral prepared by an operator. So this is how this fast finality feature look like, and so service providers have to buy this bandwidth from the operator with fast finality token, which represent the fund security collateralized by an operator, and they have to buy it from point of sales wallet that they are using in their shops, and operator prepares collateral to protect users' asset just in case anything goes wrong in the Plasma chain. And so this is how FF contract on Plasma chain works. Alice wants to buy her coffee by sending her money to a coffee shop owner, Bob, on an app built on Plasma chain, operated by the single operator. So she sends her transaction with her signature to Bob. Then Bob sends it with his signature to the operator, and the operator sends it back to Bob with their signature. Now Alice, Bob, and the operator, 3 of them's signatures are here, and Alice gets notified that. Then that means they came to an agreement that let's just confirm a finality to Alice's payment transaction with an operator's insurance to the payment recipient, to Bob. But what if the operator was malicious and break the promise? With that case, merchant can dispute the operator, claiming to the FF contract that his transaction was not included in the root chain block. This whole dispute scenario is summarized in our GitHub wiki, so please go visit and take a look at it. This is explained in our GitHub wiki. And so, summarizing up what we can do now, those are the functions what we can have in our smart contract on Plasma, but these are just mainly for transfer app functionalities. So, but what we initially wanted to do was to develop a generalized Plasma framework. So, going through all these transition of Plasma, what's coming next is PLAPS, named Plasma Group. And so in order to have more generalized Plasma, all you have to do is to deploy this special type of smart contract called predicate and on the main chain. And then you have to deploy it on the main chain, and you'll be able to build state channel type generalized application on Plasma. So supporting PG's spec, Plasma Group specs, we are thinking these ideas of predicate, what we can build, as we can implement. And we haven't done any implementation for the latest spec, but we've done around EdCon for ownership predicate, atomic swap predicate on plasma chain, and now we were just researching all these other ideas now. So we are working on the implementation and research to find out new useful standard of the predicates. So introducing one of the predicates examples, I listed swap between main chain and plasma chain. I think in the 5th row, and Ben was just talking about atomic swaps between two different plasma chains, but this is swaps between the main chain and plasma chain, and then it could be useful. It could be useful in a situation where there are too many users who want to deposit their ETH to plasma chain, and if we want to, and also there a situation where too many users who want to exit from plasma chain to the main chain, and those number of users are not equivalent, then you can swap the coins. Also, we are strongly believing in the possibility of nested predicate scheme proposed originally by Georgius around, he might be around here, on plasma.build. And for example, so which basically, for example, what the fee predicate, which basically means what we can inherit it, the nested predicate is we can inherit basic pieces of predicates and express more complex smart contracts. And what's important here is how we can combine simple pieces of predicates that have been necessary for most of the application and like common functions, and achieve the generalized smart contract in the simplest way. We've been discussing this design a lot. And yes, and so I would like to share those questions that we held internally in our team, but it might be too specific for predicates, but we are having those questions. Is it possible to develop deposit and exit functionality with those two predicates, or is it possible to solve fragmentation problem with these predicates, or is it possible to develop privacy payment predicate inside plasma cash flow design? And what's next for our team? The second thing is Rust implementation. So we are currently rewriting child chain and client implementation in Rust, so that we can test out how plasma chamber would be able to guarantee security in a various environment, and it should be more lightweighted than TypeScript implementation, we believe. And for this task, we need more implementers, definitely, and more contributors. And we are developing our plasma chamber open source, so please reach out to me if you're interested. And if you guys have any tips to manage OS open source development in more like organized way, I would like to hear that. So please talk with me about it later. So this is Crypto Economics Lab's team members. We have 6 members in total, all working remotely in Japan. And yes, thanks for listening.
You don't have to take questions if you don't want to.
You can go ahead.
I was going to ask about the pass finality design, is it fully collateralized or partially collateralized?
Fully collateralized.
So since it's fully collateralized, have you considered doing the same thing within a channel to get from 2 seconds to 1 instant request?
Yes. Yes.
Okay.
Channel with like the predicate designer. Yeah. Yeah, we have thought about it. Yeah. We are like brushing up all the designs right now, so I can't really confirm like the final design, but yeah, we've thought about it. We've thought about it. Yeah. I think
No more questions. James, don't you have a question?
For atomic swaps, can't the operator always suppress one leg of the swap? Force that leg to go to timeout? The operator can profit by breaking the swap.
Wait, could you repeat that question?
For atomic swaps, can't the operator of the plasma chain force the leg occurring on that chain to go to timeout? So the operator can profit by breaking the atonicity.
No. I understand his question, but I don't know how to answer. Do you know any answer?
Yes. So the atomic swap design is actually, you may understand it's somewhat similar to the one that you talked about. So the actual dispute resolution will have the case where only one side is filled, and in that case it just reverts to an ownership. And if both sides are included, then it swaps. Right. And it's just like there's a, you can say, oh, I only want to swap in the next block. So you wait one block, are they both there? It swaps. If not, you retain the price.
It's an escrow swap, right?
Yeah, escrow swap.
Yes. Well, if it times out, right?
Yeah.
And
So you just
times
have
out,
to
it
wait.
automatically
So
reverts.
Yeah, in a sense.
isn't this like worse than a layer 1 swap though, because the operator can force the exit game? And the exit game.
Yes, the operator can always force the exit. Yeah.
That's the trade. Why would the operator do that?
Yeah.
That loses money.
Yeah,
That's why they're actually going to do these swaps in channels.
Well, then someone else can force the exit game.
Well, the operator can exit because he's operating a state channel where he charges more.
I would ask, the plasma operator can just stop processing any transactions for a coin, so that also processes it.
Yeah.
Right.
So it's I think it's not worse than that.
So the
Even in the plasma chain without atomic swaps,
yeah. But the operator cannot generally profit from censoring a transaction in a standard just plasma send, right? The same way a Bitcoin miner can't profit from censoring a Bitcoin transaction in the general case. Whereas Ethereum miners can profit from censoring transactions, but that's a different story. In this case, the operator, if they're involved in the swap, can potentially profit from affecting its outcome after entering into the swap, right? So the operator can always force an exit game and might have external profit by doing so, depending on the terms of the swap. And is Dan around? Dan's point is that layer 2 atomic constructions are generally worse than layer 1 atomic because someone can force an exit game, and exit games are a high negative EV for the system.
So on the channel side, I would just add the caveat that you can make the period of required censorship arbitrarily long.
On the channel side.
Yeah.
Okay.
No, I think that the operator censoring a particular swap is, it has to take into consideration the net present value of all the fees, number one. Number two, you can also mask the actual contents of the swap so that you can, pre-commit, and if you actually were to not include it, then, or censor it, whatever, then you can get slashed. And, we have to do a security analysis on all of these things, but I have to say that I have not been concerned about this particular thing. But we should definitely talk about it. Because you can convince me if it's good.
The swap if the operator is a participant.
Okay, we're out of time.
Sorry.
Sorry, guys.
Great working group topic.
Yes,
later.
good work.
Yeah.
Thank you.
Oh, this. Yeah, you're just gonna have to scroll down. because it opened up in a browser tab.
Okay.
Yesterday.
Can
Oh, we could download it actually.
It's a little bit hard because it's got a lot of transitions.
Okay, it's.
Is that normal?
No, it's not. Yep.
Yeah. Okay, cool.
Oh, wait.
Do I need to?
I should make this bigger.
Just make it bigger.
You can actually full screen the view.
Is that like F11?
Yeah, or your view.
It's Control L.
Oh, awesome. Right, hello everyone. Is that good?
Yeah.
Yeah, okay. So I'm Tom Close. I'm the founder of Magmo, and I'm going to talk about state channels. So state channels is quite a broad topic. What I'm actually going to talk about is some aspects of state channel design, and in particular, some ideas that have been useful in the recent attempts to come up with a unified state channel spec. Before I do that, I'm going to talk just for a little bit about myself and Magmo, because I realise there are a lot of people in the room who have never met me before. And so start off with, hi, I've said this already, but I'm Tom.
Hi, Tom.
Hi, Tom. Hello, Tom.
Thank you, everyone. So I live in Oxford. I've recently moved back there after spending a couple of years in San Francisco, both awesome places in very different ways. So I've been working on state channels since late 2017. Before that, I was part of a startup. So I joined the startup as the first engineer, worked for them for 4 years, ended up as a VP engineering. That was really exciting. Moved out to San Francisco for that. It was food delivery, not that that matters, but that was kind of a load of interesting problems in terms of vehicle routing and stuff, probably digressing too much. And before that, I did a PhD in quantum computing. And if you look at that, you'll probably realize that I have an attention span of about 4 years. The other thing that you'll realize is that I've done both research and development, and that's the one thing that I've really enjoyed about joining the Ethereum community, that you can be doing these hard research company, which means we do both research and development. I'm going to very quickly talk about both sides of those things. The first piece of research we put out was in June 2018, which is Force Move Games. And what this paper was about was a way of formulating some update rules for state channels. And I guess the approach was that you think about what happens in a state channel in terms of a state machine, and the job of the developer is to write the rules that define which transitions are valid and which transitions aren't. And the job of the framework is to take on everything else. So that in itself wasn't particularly innovative, but one of the things we did, which I think was the first time to do this, was to do updating state channels via turn taking. So you do a round robin style, people take turns to sign updates. And that's one of the things that I'm hopefully going to explain a little bit more about today. That's an idea that has begun to, I guess, take a bit more root in the community as we've tried to standardize state channels. The latest thing we've done is Nitro Protocol. So whereas Force Move was all about how state channels update in direct channels, where we have an on-chain deposit on-chain, we're just two of us are updating to, or in fact, it actually scales to n parties, so n of us are trying to exchange things. Nitro Protocol is how to build those state channels out of other state channels so that you can open and close state channels on chain. So the idea is I have a deposit on chain with an intermediary. Through that intermediary, I can open and close channels with other people without having to redeposit and stuff on chain. The one thing that this does is it uses Force Move as the only update mechanism for channels. So the channels that fund other channels are also just channels themselves. And then on the development side, in November 2018, released a rock, paper, scissors game. That was a very simple proof of concept for Force Move Games. You can play that online today. More recently that we did tic-tac-toe. Now tic-tac-toe isn't a big upgrade over rock, paper, scissors. Arguably it's not an upgrade at all. But the thing that this did was show that we could write a wallet that could support multiple different applications. And the hard thing about state channels, or I guess this is like the state channel implementer's curse in some way, that state channels are kind of easy to explain. They're very simple concepts. It's kind of easy to write the code on chain, and all the complexity, as far as I can see, comes in writing the off-chain code. So the things that we've done here, they're just direct channels, but they do handle the dispute case. So if you go on tic-tac-toe with a friend today, you can play against them, you can deposit on chain, one of you can dispute, the other person's software will notice this, and they will cancel the dispute. And then finally, what we're working on is beginning to upgrade this wallet to handle Nitro. So we're like halfway through, we can do ledger channels, which is like one person, one deposit, multiple channels. We're not quite yet at the stage where we can do virtual channels, but I think we should be there in the next couple of months. Okay, so enough about that. What is a state channel? So I guess everyone here probably has an idea of what a state channel is. I'm just going to go through a very quick example. Probably all seen this before, so I'm going to rush through it. So this is Bob, this is Alice. They want to do a lot of transactions off-chain. This example is actually a payment channel. So they start out by exchanging some agreement about how funds on-chain are going to be split. They then deposit their funds into this contract on-chain, which I'm going to call the adjudicator. They then send multiple updates to each other off-chain. And so like they're agreeing that the funds on-chain should be split differently, so they're kind of moving funds back and forwards. And then when they come to the end, so they can do that like hundreds of times, like only limited by the speed they can like sign transactions and communicate with each other. This is where you get the speed of state channels. When they've done that, they take the final outcome, they send it to the adjudicator. Of course, the adjudicator doesn't know it's the final outcome, so you have to start this exit game, a timer starts. During that time, the other party can produce a later state. When that time's out, the outcome becomes finalized on chain, and then you can split the funds. That's a very, very simple state channel example. So what's a state channel? So just giving you an example, what I'd now like to try and do is start thinking about how would you actually define a state channel. And this has been kind of interesting, especially as we've been trying to unify our different state channel approaches. It's easy to like, when I say that state channels are a bit like hardcore pornography, in that like you know it when you see it, but it's difficult to define. And so like trying to find something that like encompasses all these different ways of doing state channels. So this is what I'm going to attempt to do now. And this is just like a working definition. It was a little bit useful in the state channel workshop a few weeks ago. So a state channel is a device that enables a fixed set of participants to execute a protocol in order to reach an outcome. Okay, so two important things there are a fixed set of participants and this outcome, but I haven't said what an outcome is. So for the purpose of this, an outcome is just some string of bytes. But an outcome typically corresponds to one or more intended effects, and these effects will occur if the channel is funded. So that was all a little bit abstract. Let's look at an example. So this is an example from the thing I did earlier. So in this state here, the outcome is the bit that says Alice gets 8 and Bob gets 2. And that outcome could be encoded as a string of bytes using something like ABI encode. One of the things that your state channel framework needs to do is to explain like what is the data format, how are we gonna like encode these outcomes. So the effects from this, the intended effect is that Alice receives a transfer of 8 from the contract holding the state deposit, and Bob receives a transfer of 2. So this is the effects of the things that should happen on chain from this outcome. And the funding, for this to happen, the state deposit contract must hold at least 10 ETH. So the point here is that the outcome and the funding are separated. Alice and Bob could totally start a channel, start signing things, produce this outcome, maybe even finalize it on chain. But unless they've funded it, unless they've put the money in the adjudicator, it's all for nothing. No funds are going to move on the chain. So I've already said this a bit, but an outcome becomes finalized when it becomes registered against the channel on the blockchain, and only one outcome can be finalized per channel. So registered against the channel is like a bit of a vague term, but like something like this seems to exist in all state channel frameworks. There needs to be some way of saying like, this is what happened in this channel. Okay, so I've already seen one way that an outcome can get finalized on chain. So in that first example, there are loads of things, they set the state, there's a timeout. There's typically at least one more way that an outcome can be finalized on chain in a state channel framework. And that is the collaborative close. So for the collaborative close, what typically happens is one participant sends a special message to the other participant which says this is the final state of the state channel. And it's important that this is like explicit, it's not just like another state. The participants need to know they're signing this thing. The other participant like double signs it or something. Once you've got this double signing sort of final state, as it were, that can be submitted to chain. Instantly, it gets accepted and the coins are split. So this is like the fast checkout stuff that we're talking about that maybe can't happen on Plasma, but maybe can in some things. Maybe can't. I don't know.
If they use channels.
If they use channels, yeah. Okay, so the final thing that we've talked about state channels, I think this is another important property of state channels, that you have this exit criterion, which is like at any point when a state channel is running, it's possible for any participant to finalize an outcome within a finite time, regardless of the behavior of the other participants. This is like about counterparty risk. In a state channel, you're locking up funds in a way that is somehow accessed by two people's signatures. And you need to be sure that like two or more, I mean, you need to be sure that one person can't prevent you from ever withdrawing those funds. And this is like the sort of property that keeps that safe, or something like this. So why are outcomes important? Why am I like introducing this notion of an outcome? And this is really about like the logic of state channels. So in a state channel, the sort of reasoning you do is like the states that I hold, the things that have been sent to me and the things that I've sent to other people mean that I can attain this outcome on chain. And this outcome means I'll get these effects. Therefore, my position at the moment can be treated in somehow equivalent to these steps. So like if this situation means I'm going to get an outcome where I can get 8 from the adjudicator, that means that this situation is like worth 8 to me. And that's basically kind of, this is like the counterfactual logic kind of reasoning, pretty much. Like if I were to take this to chain, these things would happen. Therefore, I can sort of behave as if these things have happened. So in terms of thinking about outcomes, it's important, as I said, it's important to think about like, what have I got? What's my system look like? And calling this thing the system view, and I'm calling it the system view because it's different for each participant. There is no like, in a state channel, there is no like universal state of the system. It's quite possible that somebody has sent messages other people haven't received, or has sent messages to some participants, and we need to capture that when reasoning about how state channels work. So what's included in the system view? So definitely the state of the adjudicator. This is the public knowledge that's available to everyone on chain, and the stuff that you need to care about is there a challenge going on in your state channel? Has your state channel already been finalized? Is there money held against your state channel? So like the adjudicator state, the state of everything in the state channel system on chain, is an important component to understanding the value that you're holding. Another thing is your private resources, any private keys you hold, in some cases like secret information that you might not have revealed to other people, like hash lock payments. You've got a pre-image to a hash that's going to mean that you can pay someone some money. The states you've received are clearly important. People send you things, those things allow you to do things, they've got signatures on them. Like that's the fundamentals of state channels. But also the states that you've sent are important. As you'll see as we go through, what typically happens is when you send states, you give up certainty over the state of the system. You like give people options to do things and like use those states against you. New concept, a finalizable outcome. So an outcome is finalizable for a participant if that participant has an unbeatable strategy for finalizing it and knows that they have an unbeatable strategy. This just stopped. Oh no, it's back again. Sorry. So What do I mean by an unbeatable strategy? What do we assume here? So typically we assume that the chain isn't being censored, but like as you increase your risk models, you might want to start factoring that in. What we don't allow as an unbeatable strategy is getting something first. You always assume that you can be front run. If somebody else has another state that could beat your state, you don't have an unbeatable strategy because they could always get to the chain first. So that's like explicit in this, like it has to be the state that like you can't think. The unbeatable strategy might involve submitting a final state and instantly checking out your coins. It might involve submitting a state and waiting for the challenge timeout and knowing that nobody can beat your state. It might even involve submitting a sequence of states, knowing that no one can beat it eventually, and eventually you'll get to a thing where you can obtain that outcome. So finalizable outcomes, if you have a finalizable outcome, you have some certainty about what's going to happen when you go to chain. An outcome is universally finalizable if every participant of the channel has the same outcome, the same finalizable outcome. So here's something that's just true about finalizable outcomes. If your channel isn't finalized already on chain, exactly one of the following things is true. One participant has one or more finalizable outcomes, that's the one many. More than one participant has the same finalizable outcome, that's the many one, or no participant has a finalizable outcome. And this follows just from the definition of finalizability, because if two people held different finalizable outcomes, then they couldn't both have unbeatable strategies because they'd be getting different things in there. So like this is just like a property of how we've defined finalizable outcomes. But it's kind of interesting, and you'll see that as channels go through, you typically merge between these states where like everyone has a finalizable outcome to like people losing that, to one person having maybe a couple and has an option, and then like it sort of goes on. Okay, so in the third situation, no participant has a finalizable outcome. I want to say that this is like a bad state. In fact, when I was writing this talk, I thought this was a completely bad state. And then I realized as I was writing it that it's not totally bad all the time, but we'll just like, I'll come to that a bit later. It's generally a bad state because in this state, none of the participants is in control of the situation. And that's pretty bad for state channels. What that means is the chain needs to decide, but there's no like deterministic way, like there's no like set way, there's nothing that's definitely going to win. So typically that means that it depends on the order at which you submit things to the chain or some other weird factor. And that means that you have a race to the chain. And this is bad for state channels because the whole point of state channels is that you want to keep things off chain. And if you ever get into a situation where you're incentivizing people to go on chain, that's kind of bad. You've begun to lose your scalability. And so I'm going to call this situation chanarchy. And we tend to want to avoid chanarchy because chanarchy is bad in state channels. This is yeah, as I said, you don't want to disincentivize people.
I have a question.
Okay.
Are you taking them or should I wait till the end?
Could you wait to the end? I'm just mid-flow. Okay. So as I said before, like I thought that when you had when no one had a finalizable outcome, that was kind of bad, and that was chanarchy. But actually, I think it's a little bit more subtle than that. And to see that, I'm going to introduce this like this is like the co-concept to finalizable enabled. So an outcome is enabled for a participant if they have no way of preventing it from being finalized. So it's like the rights you've given up. And there's this relationship between finalizability and enabled. So exactly one of the following things is true. The participant has at least one finalizable outcome, or the participant has at least two enabled outcomes. Why is it not possible to have one enabled outcome? Well, if you have the exit criterion, that means that anyone can drive the system to some outcome. If you have only one enabled outcomes, that means you can prevent all other outcomes, and you can like drive the system somewhere, which means you have a strategy for finalizing that one single outcome. So if you have a single enabled outcome, you have a finalizable outcome. So like participants are either in the like two or more enabled outcomes, or they have at least one finalizable outcome and have control. So this is a working definition of Chanarchy at the moment. Might not be quite be this. Like, there's definitely something here, but I'm not sure if it's exactly this thing that I'm saying. So Chanarchy occurs when there are at least two outcomes that no participant can prevent from being finalized. And you'll notice that no participant having a finalizable outcome is a necessary but not sufficient condition for this. Equivalently, Chanarchy occurs when there are at least two outcomes that are enabled for all participants. So this is the thing where, like, basically it's about people being able to prevent things. So let's have a little example. So I'm going to introduce one more new concept, a lot of new concepts, and an instantly finalizable outcome. So an outcome is instantly finalizable if a participant can finalize it without delay. That's like this thing I showed you with the collaborative close. It's that thing. So one thing you'll notice, in a time-independent system, once any participant holds an instantly finalizable outcome, no other participant can ever have a different finalizable outcome, because that instant finalizable outcome is just presenting it as an unbeatable strategy. So basically what this says is, once you've signed one of those, this channel is closed. Once you've signed an instant checkout, the channel is done. You know, like, you're done. You have to stop and you have to sort of start again in a different channel somehow. So what if two instantly finalizable outcomes exist? So this could totally happen. Alice and Bob could just sign this. They probably shouldn't in the protocol, but what happens? You guessed it. That's bad. Both of them have instantly finalizable outcomes. It's a race to the chain. Which one gets there first? That's kind of bad. So I'm going to give a few examples about possible update methods for channels. So there are different ways you can define how states, 5 minutes. Ooh. Okay. I'm going to skip over a few of these. There are different ways how you can define how states update. One of them is that everyone has to sign everything. So I wanted to go through these, analyze what the finalizable outcomes are. So in this case, A, B, and C have signed state 1 with outcome omega. That's the turn number, the outcome, and the signatures. A, B, and C all have a finalizable state omega, finalizable outcome omega here. What happens in this case? A progresses. So B and C still have omega finalizable. To do that, they can just withhold their signature. A has enabled omega primed as well as omega, because A has given up something by signing something. This is a weird one. This is the one that made me realize that Chanarchy was actually more to do with enabled outcomes. Here, what's happened, A has omega and omega primed enabled, B and C have omega and omega double primed enabled, but it's kind of okay because people can still prevent things. There aren't two states that nobody can prevent. So in this situation, you'd hope that at some point, A would either sign that or B and C would sign the other thing. This is one of the weaknesses of this particular system where everyone signs everything and there's no way of unilaterally progressing the state. And then you can also have this case where you move to a new state that has the same outcome, because these are outcomes, not states. So I wanted to say that this is just to highlight that you have states, and I'm ignoring the state part. I'm just focusing on what that state means to you. So this is interesting. Everyone signs, and you can unilaterally advance state. So you can have this situation where A advances to omega primed, and if we take that to chain, A will get omega primed, but B could go somewhere else. That's a problem because, like, we've got this race condition, we've got Chanarchy. The other thing that was that I brushed over here is, like, in terms of figuring out what's actually enabled for you, you sometimes have to think about where people could move as well as where they've actually moved. So here, if this was also a possibility, anyone could also move to that state and no one can stop it. So I did want to talk about turn taking quickly. Let me just think. Yeah, so in turn taking, basically you say that each state has to be signed by the participant whose turn it is. So, like, if there are two of them, I sign the odd ones, you sign the even ones or something. So this is kind of nice. In this situation at the top, what can we say about A? Well, A has the finalizable outcome omega 3. A can finalize that by withholding their signature. Like if this goes to chain, eventually the system will be driven forward into the omega 3 state, and then the only person that can sign the fourth state is A. So A has a finalizable outcome here. What does B have? So to figure out what B has, B is signed omega 2. So we kind of have to think about so B can't prevent omega 3. If A could move here or here, B can't prevent these either. And actually, even though C has signed that, B can't prevent C from signing something else and enabling these ones. So to figure out what you have enabled, you have to kind of play the state machine through until it's your turn again. And you can figure out some sort of value from this. MFN is China key. I might just stop here. Let me do this one slide and then I will stop. So I guess to try and bring this together a little bit. So these are ideas from the Nitro Protocol paper. Why do we introduce these ideas? Because they're important in reasoning with state channel networks. So state channel networks involve the opening and closing channels off chain. So you're funding one channel from another channel. And this is where you get the power from state channels. And this is the observation. Opening and closing channels off chain is just transitioning between two different sets of universally finalizable outcomes, which have the same on-chain effects. So what this is saying is when you're opening and closing channels, you're just rewriting the situation. And that's actually, I think this is the basic logic that applies to all state channel networks that do this in some way. But it's kind of nice to think about this because then you can begin to construct proofs that things are secure. So how do you know, this is from the Nitro paper, how do you know that you can open a subchannel? So I'm not going to explain this completely, but we have a channel on chain, A and B. They want to open this channel Chi. So they're going to do these operations, and each of these operations moves between a finalizable outcome where A gets 5 and B gets 5 until this point, and then they're in that channel and they can start progressing the channel in a non-finalizable way. And to do that, it's important that you have this universally finalizable state to the front and the end. Anyway. So the open questions. So here are some open questions as we're thinking about in state channels. One of them is turn taking enough to run any protocol? It seems like with turn taking you have certain nice properties. You sort of need the property that everyone gets a turn within a finite time, otherwise you get into that China key situation. But is this enough? Or do we need the thing where you can have things like A, B, C, B, C, A, that sort of thing to run certain protocols? What's the best way to handle time dependence? So time dependence was something that, at least in Force Move and Nitro, we ruled out at first, because it becomes a lot harder to reason about which outcomes are finalizable when you have time dependence, because you've got this extra factor of am I going to get to the chain in time? Are things going to change before I get there? So there are basically two ways you can put time dependence into this system, and I think you probably need both of them. And the other big question is, what level of time dependence can we handle? It might be that there's some time-dependent things which is just hard to do in state channels because of the incentivization and can I get to the chain in time to enforce this if I need to? So these are some questions that I'm thinking about. They're also feeding into this state channel standardization process. Be interested to discuss these with people. And that's it. Thanks for listening.
No, you answered it. I should have waited till the end of the presentation. You answered it with the Cherokee thing. What? No, but so people know beforehand with the working group. Okay, so some feedback I got yesterday was to announce the working groups beforehand so people know for later, but we have more presentations. There's 3 working groups. You're welcome to propose another one. There's more than enough rooms. The first one is generalized plasma, led by Kelvin. The second is state channels with Lane from Connext. And the third is synthetics on Plasma with Carl Flörsch and Dan Robinson. Flörsch, I don't know. Also, announcement, Chainlink has graciously offered to sponsor the day 2 after party. They've rented out the top floor of something that I sent in the Telegram channel. Duke of York, which is a 10-minute walk from here. It's from 6 to 9 p.m.
Okay, sorry. Hi everyone. I'm Xuanji from L4. I'm here to talk about payment channel networks with focus on scalability. So I'm gonna start off. These are the topics I'm gonna cover today. A review of payment channels, mechanisms for constructing payment channel networks, how many different networks differ, constructions differ with each other, the concept of virtual channels and offloading, and channels on Plasma. So this section is supposed to be about how kind of direct payment channels work, but we've had a lot of that today. So I'm going to assume you have absorbed all of that. I'm just going to use this slide to show the kind of the notation that I used throughout this talk. So I draw a box around the smart contract that we use to that implements the contract that holds the actual money that is in the state channel, so the 20 ETH, which we call the state deposit holder. And then these are the messages that are exchanged off-chain. These are the signed messages. And these are the people, Alice and Bob. So for our purposes, what we need to know for this is that a state channel exit game's purpose is to kind of determine what is the latest signed message. So for example, if both Alice and Bob are cooperating and online, they can just tell the contract what the latest state is, and this will be the cooperative close or cooperative withdrawal that Tom talked about. If not, there's a timeout-based exit game, etc., etc. Okay, yeah. So now I'm gonna talk about channel networks, and I'm gonna start from something maybe a bit more basic, just to kind of be sure that we're on the same page. So the realization, the context, the setting in which we try to do state channel networks is that we have multiple direct channels on chain. So here we have an Alice Ingrid channel and Ingrid Bob channel. So there are 3 people in the world, Alice, Ingrid, Bob. They kind of have these channels. And let's suppose that these are the balances. So for example, in the Alice Ingrid channel, Alice owns 2 ETH and Ingrid owns 2 ETH. So the starting point for channel networks is to see that suppose Alice pays Ingrid 1 ETH, and then maybe sometime later Ingrid pays Bob 1 ETH. This is kind of equivalent to Alice paying Bob 1 ETH because Ingrid's total balance across all her channels has not changed. Alice has lost 1 ETH and Bob has gained 1 ETH. So this is a cool library I found on Twitter to kind of represent 2-party payment channels. And this shows Alice paying Bob 2 ETH through the hub and going back and forth. Right, so Ben showed you this example today, right? So kind of like, I think the point he was making and the point I also want to make is that not all payments are possible only off-chain. So for example, in this case, you guys worked out that the maximum that Alice can pay Frank is 2 ETH. And then we can kind of see that kind of the way I personally think about how to compute these things is that, for example, you can compute an upper bound on how much Alice can pay Frank by just finding a set of edges that disconnects them. So if any payment that Alice pays Frank has to pass through this blue line, and you can see that out of the 3 edges, the payments on the leftmost edge at most 1 beat can pass, and on the rightmost edge at most 1 beat can pass, and in the middle no beats can pass. So we're gonna get back to this later. But this is kind of how I think about the payment capacity constraints that happen in channel networks. So given that not all payments are possible in a payment channel network, what can we do about that? Well, if a certain kind of payment is not possible, we off-chain in the channel, we have to go on-chain, and we have to actually do a expensive, slow, etc., Ethereum transaction, which kind of sucks. In general, we call those things on-chain rebalancing. So like for example, let's use a smaller example. In this case, the amount that Alice can pay Carol is 0 because there's no beats that can slide towards the left. So but that's not because Alice has no money. Alice actually owns 2 ETH. It's a minor whale, and what she can do is transfer those ETH out of one channel and move it to the other channel. So this is the new state. Kind of the beats have hopped over there, and this transition requires an Ethereum transaction. Sorry, this transition requires an Ethereum transaction, but now Alice can pay Carol off-chain. So that's called on-chain rebalancing. There's also cases called off-chain rebalancing where, like in this case, Alice cannot pay Carol, but if you transition the state off-chain to this, so it's kind of, the orientation kind of changed. Alice can now pay Carol one ETH. I mean, this example is really small, so it you have to imagine, you should imagine these things happening in a bigger, more embedded in a bigger, more complex network, and then you'll see that there's some chances to do off-chain rebalancing in there. So going back to the cut example I started with, kind of you can see that if Alice wants to pay Frank, more, like possible on-chain rebalancing could be Carol moves some of the money from one of her channels to the other, so that this cut is no longer so constraining. Yeah, and that's kind of the, what do you call it, the min cut max flow theorem, or the weak form of it. Yeah, so that's kind of the consequences of building payments on top of a channel, on top of a payment channel network. So the next section of my talk, I'm going to talk about kind of the specific mechanisms that we use to construct these things. And so the reason that we want to go into this instead of treating it as a black box, well, one of the reasons is that there's many projects, and they kind of, most of where they many kind of either state channel or payment channel projects, and a lot of what they differ in is how they construct these routed payments or payment channel networks. So I'm gonna go through 2 of the axes in which they differ. So direct versus indirect dispute, and rent-a-path versus routed payment. So to kind of get into this section, let's rewind back to the example that we started with, where Alice paid Ingrid 1 ETH and then Ingrid paid Bob 1 ETH. So we don't actually want to do this because Ingrid can just take the ETH and be happy about it. So there must be some mechanism for which this thing is atomic. Like either the whole chain of updates goes through or it doesn't go through. So the question is, how do we ensure atomicity of these updates? And like, remember that these are in general separate channels. They are not a priori aware of each other's existence. The only thing is that Ingrid is a common participant between them. So how do you ensure the atomicity of this thing? Well, I think a general strategy that many mechanism designers, many people working in crypto use again and again and again, very common theme, is that you do it in conceptually 3 steps. You lock one of them in a, this lock represents it's a smart contract basically. You lock it into some condition, so it neither belongs to Alice nor Ingrid, but its ownership is governed by some set of other set of rules. You do the same for this, and then now you can transition the 2 states atomically through some as yet unspecified mechanism. So yeah, very common trick. So I'm going to go through 2 of these mechanisms, 2 very popular mechanisms. So if you think about in crypto, how do we do these things atomically? There's like hashes and signatures. Those are 2 very common things. And so I think if you pose this problem to someone in Ethereum who has not thought about payment channels before, they'll say, okay, I'll try something with hashes. So I feel like that's the most natural solution someone would first stumble upon. So let's see what that looks like. So this is the name of this design is called hash-based direct dispute. My invention for the name, but anyway, so we now have to specify what the lock means. So what governs who owns these things. So in the hash-based direct dispute, there is, okay, sorry, going back a bit. So if the state of this coin is that it's under a lock, this means that the exit game of the, suppose that you place these locks, but you don't do the off-chain the transition so that they now move to the right. Then the state channel exit game will run, and it will only determine that these things are in the locked state. So how do so at that point, how do we, at that point in the exit game, how do we atomically move them into an unlocked state, into the correct unlocked state? So for hash-based direct disputes, there is some storage, some 32-byte storage slot somewhere, and the condition for removing the lock is that you have to review the pre-image of a certain hash within a certain amount of blocks. So it says you have 5 blocks to do it. Oh, you have 4 blocks to do it, and you haven't done it yet. It's getting closer and closer. Now the hash is reviewed. And then so the hash is reviewed, so the smart contract says that if the hash is reviewed before this deadline, the coins go to the right. Otherwise, they go back to the left. That's hash-based direct disputes, and that's kind of the project that most directly implements this is called Sprites. Yeah, so to start kind of comparing the different mechanisms and how they differ, before that, sorry. So one very interesting thing to note is that the way this direct dispute mechanism relies on like non-local states. So these two lumps of ETH, they have to observe the same storage slot. So in particular, this thing, such a trick cannot be done in Bitcoin today because like 2 Bitcoin UTXOs cannot refer to the same, cannot refer to another common stateful thing as a spending condition. So direct disputes are not possible in Bitcoin. So if you look at any of the payment channel literatures around that are implemented on Bitcoin, they normally use this trick where the timeouts are they refer to 2 different slots and they stack the timeout so that if this hash gets revealed, you have 5 blocks to kind of reveal it in that hash. But it means that the timeouts are kind of longer than strictly necessary. And this is a fun fact to ask Bitcoin maximalists about. It's like, how do you deal with this? And like, they give interesting answers. No, but I think it is a kind of a limitation of the kind of constraints that they have set for themselves, that you get this problem in payment channels. So kind of that is one of the axes. What I've called direct dispute versus indirect dispute. So that basically means do they observe a common source of truth for the outcome for kind of whether the thing happened, or do they not do it? Yeah, and these are the projects that choose to do it differently along this axis. So to kind of explore the next axis as to how they differ, I'm going to think of, is there any other way to solve this behind hashes, let's say. So I'm going to go through a second design, which I call the virtual payment app, or you can call it the virtual payment channel, the virtual two-party payment channel. And the idea here is that okay, so in this, right, so this is, in this case, Alice has put 1 ETH in, Ingrid has put 1 ETH of collateral, and the same for Ingrid and Bob. And they both observe a common thing as before. But instead, now the difference is that instead of the common thing being a binary outcome, like did the hash get revealed or did it not get revealed, it becomes like a richer outcome that represents the kind of all possible states that the payment could have taken. So Alice put in 1 ETH, Bob put in 1 ETH, the route is fully collateralized. So it could go anywhere from Alice owning 0 and Bob owning 2 to Alice owning 2 and Bob owning 0. So what the virtual payment app design does is that it says that at some point, this thing in a dispute, the thing that they reference should, the thing that they reference should resolve to an outcome that says that is the directly in the thing that we want to achieve. So in this case, Alice's balance is 0 and Bob's balance is 2. And then the contracts that the contracts that are locked up in the individual channels look at this outcome and kind of route it as though that was a single payment. So so for a single payment case, all the Alice would pay Ingrid 2 ETH, so it goes like this, and Ingrid would pay Bob 2 ETH, so it goes like this. So that's how a virtual payment app kind of works. And so comparing the difference between this and the hash-based model comes to a pretty important difference around locking models. So locking models is the idea of how are the states locked? What are the differences in the ways we have locked these two different things? So to be more precise in the question, we want to say when are the locks released? So in the hash-based example, they are released when a hash is revealed. So and a hash revelation constitutes the payment. So they are unlocked. They are locked per payment. So you lock it and then you do one payment. Whereas for the second one, the virtual payment channel example, they are kind of locked for some amount of time, and at the end of that period of time, as I've described it, this thing resolves to something. So it's most natural to think about it as being locked for some amount of time. Yeah, and the kind of the difference in functionality between them that I'm getting at is that, for example, for the virtual payment channel example, let's say you lock it up you lock this thing up for 5 days. Alice can send Bob one payment and then send another payment, and then Bob can send it back. So you get to use this channel for 5 days, and then so you're really kind of renting the path from the intermediary. You're making the intermediary lock up their collateral for some amount of time instead of for some amount of payments. So, and the reason this is kind of important is that kind of we can use this to, we can use the time-based model to emulate the payment model by making the timeouts very short, but you really cannot really go the other way, because for the per payment model, the intermediary has to be kind of involved every time you want to make a new payment along the same path. So that's kind of the other major different axis by which these projects or these designs are differentiated, I would say. So the routed payment is the hash-based one. You contact it, you say, I want to send one payment, and then done. Now your interaction is over. Whereas for rent a path, it's more naturally, I want to rent this thing for 5 days, and for these 5 days, I can use it however I want. Right. So in this section, I want to talk about why I chose the word virtual payment app or virtual payment channel. So kind of what the word virtual means. So I think there's no one standard definition, because the terminology came up in Perun, and they originally used it to refer to something very specific, but now I think it got a bit more general. So for me, when I say virtual channel, I really wanted to kind of mean that we implement something with a virtual payment channel kind of implements the ideally the exact same functionality as a payment channel. So in this case, we Alice, Bob, Carol, and if we want Bob to be the intermediary and we want to set up a virtual payment channel between them, we want to be able to treat it as though it's like this for the amount of time for which it exists. So in this thing, like Alice, for 5 days, Alice can do whatever they want with this bead over here, move it back and forth. So it behaves as like a payment channel for them. So that's the terminology that I use for virtual X. It behaves like that. And one of the research problem that I wrote down in my section of the document is how do we build virtual channels around these things, like topologies like this, because you can see that Alice can pay Dave 1 and Carol can pay Dave 1, but they can't do it at the same time. Okay. Right, so moving on to channels via Plasma, so a rather different topic. This is a specific way to build payment channels that are funded on Plasma. And I'm going to try to abstract over the Plasma contract as much as possible. So on the blockchain, there is some Plasma contract, and we're going to say that there's some off-chain state for the Plasma contract, which is, in this case, who owns this lump of ETH, Alice, Bob, and then Dylan. The specific way that I propose to implement payment channels on Plasma is that instead of just locking to specific EOAs, they can also lock to a contract address. So it locks to this thing called M, and M turns out to be the create to address of a well, it says multi-sig, but it's a create to address of the state channel. The state channel adjudicator contract, or the state channel deposit holder. And the purpose of the Plasma contract is to determine who is the rightful owner of that lump. In this case, it's the thing is owned by M. So in the Plasma dispute, in a Plasma exit game, the Plasma contract will pay out to the multi-sig. And then there's a separate kind of exit game for who owns which thing in M. So let's say this is we copy and paste this from just now. It's this way. Then the multi-sig the channel then pays out to Alice and Bob. Right. So the kind of thing that we want to get out of building this thing is that we want the optimistic case to resolve without this whole process. So it means that the lump has to be able to get out of M and into someone else. Let's say Fred. So for this reason. The conditions for locking it into M, well, M means the lump belongs to M, and we have to withdraw it to M. But we also have to specify what signatures are allowed to create a valid Plasma transaction that send it to Fred. Right. So kind of the advantage that we get out of this is that for a payment. Remember the payment channel network example I said, where you have to do rebalancing to do certain kinds of things. If all these channels were funded by Plasma, you can kind of rebalance all of them with one single Ethereum transaction. So one Ethereum transaction does like 10 Plasma transactions, and the 10 Plasma transactions rebalance all these things. So that is I think that's a really important feature for channel networks. Like it's a big order of magnitude difference. Like it's just a big difference between whether rebalancing your channel network is this expensive operation, or whether it's this relatively cheaper operation. I think I'm out of time here, so I'll just stop and take questions. Yeah, thank you. Yeah. Okay. Oh, whoops.
Hey, hello everyone. So I'm Xiaozhou Li from Celer Network. Today I'm going to talk about the state channel contracts and protocols we developed in Celer. So first I would like to share some our experience in running a real state channel network on Robston testnet. So a few months ago, we did a testnet campaign and on Robston, and so the Edge node are our Celer X mobile app on Android and iOS, and the payment relay nodes we implement and develop ourselves, hosted on AWS. We call it Off-Chain Service Provider, or OSP. So we run it like actively for 3 months and got data activities from real end users, users from 88 different countries. There are about more than 12,000 channels open, and more than 190,000 off-chain Gomoko games were played every month, and 4 million off-chain transactions monthly. This includes the game moves and the payments related to it. So these are some okay numbers. These are not particularly high. It's mainly bottlenecked by our marketing push because these numbers have to be generated from real users. And these are all based on our previous V1 implementation. We actually run into a few performance issues and learned a lot of valuable lessons from it. And what currently in our open source repo is our V2 implementation, which we have made a lot of improvements. And today I'm going to talk about this, our new implementation and the design rationale behind it. So because for the most important goal of the state channel, of course, is high performance and cost efficient. And we have different design principles. Of course, priority 0, which is actually a requirement, a must-have requirement that cannot be compromised, is security and trust-free. I'm not going to details of it. And then the priority 1, the number 1 priority is to minimize the on-chain footprint, minimize the number of transactions, and minimize the gas cost of each transaction. So we have been trying very hard for this. And then the priority number 2, from our perspective, is to minimize the relay node on-chain interaction. We want to push the complexity to the edge because that's the best way we can really scale out the systems. Oops. And the priority 3 is to minimize on-chain non-transaction interaction, like a view calls, like event watching. Though this do not incur like real gas costs, but if you're running a large-scale high-performance systems, each of these on-chain view, like event watching, is still much more expensive than your pure off-chain communication. Then it comes to our priority 4, which is of course also important, is to minimize the off-chain communication overhead. So basically, all these priority and trade-offs are based on our real cost analysis, like which operation cost more, especially if you're a service node sitting in the middle of the payment network. So our design choice, our most important design choice is to decouple the payment channel and the app channel to make it 2 separate contracts so that we can easily scale. Because if you think about the network, only payment needs network. So the application itself does not need network because you don't need to relay the payment states. And we choose to use protobuf because it's language neutral. Because, for example, our on-chain contract of course using Solidity, and our off-chain, because we want it to be large scale and high performance, we use that as implemented in Go. And it's easy to be extensible, and it's easy to develop. Okay, so the payment channel. So our payment channel, which we call Celer Pay, is a generic payment channel. So it is a networked 2-party channel holding crypto tokens, and it naturally supports multi-hop generic payment. Multi-hop payment with generic conditions, which is the payment result can depend on the app logic, like the condition results. And each of the payments only needs to be set up once and then shared by all applications. And here, so we did some optimization so that for, say, a client, when a client comes, it only requires 1 single low-cost transaction to open channel and add funds from both parties. You don't need to deploy any contracts or any other additional transactions to open the channel. You can open the channel pretty fast, and then this channel can be shared by all the apps. And the relay nodes never needs to look at the conditions, the app logic. The payment relay nodes only care about the payment. And you can welcome to check out our code. And the app channel, the generic state channel apps, they only require like two very simple APIs in order to work with our payment channel. And there's no other restrictions, say the number of parties, how do you progress your app states, this logic, etc. So these are like these two constructs are decoupled so that it can easily scale. So now going to some more details about our payment channel. Our payment is actually a duplex channel so that each party can send payments to its peers concurrently. It composes of two simplex states. And so A and B interact by co-signing the updated simplex states. And our state channel, it includes these fields like a channel ID, like the peer from address, the sequence number, the unconditional transfer amount, which is always increasing, and the pending pays, which is pays that are not finalized because these payments are usually carry conditions and timeouts, for example. So the list of the pending pays and some other helping metadata like last pay deadline and total pending amount. Then for each pay is unique and immutable globally. So adding for payment node to relaying a pay is simply to add this the hash of the pay to the pending pay list of the state channel. And here the construct of the conditional pay. The most important fields are the list of conditions, which are the how the pay will be resolved, and the transfer function related to this pay, and also the resolve deadline for like when will the pay be timeout. And these are some other helping fields that I'm not going to go into detail today, but I'll have backup slides for that. I'll see if I have time for that later. And for each pay, as I said previously, each pay carries a list of conditions, and here's our payment condition. Each condition carries a condition type, and currently we have 3 types of condition. It's either a hash lock condition, or a condition based on an already deployed contract, or a condition based on a virtual contract which has not been deployed yet. And it carries 2 arguments, like the query if the condition is finalized, and to query if it is finalized, what is the result of the condition. And with the list of conditions as input, we have a transfer function that has you can implement a different transfer logic based on this condition. For example, it can be a Boolean condition, which means usually it means this payment will either happen or not, either pay the max amount or pay 0 based on the condition results. And the condition can also be a numeric condition. For example, the condition will return value, saying that, for example, here the max amount is 10, but the what you actually pay will depend on the result returned by the condition. Say the max is 10, but the actual condition result returns 6, then you only pay 6. Okay, so with all the constructs I previously described, I'll now go over like our off-chain protocol of how to send and relay and settle conditional payments. For example, here A wants to send the D a conditional payment, pay AD. For now, we assume that it is a transfer is a Boolean logic, which we think is the most common logic. And by sending a payment pay AD, A will ask B to cosign a new simplex state. Just add the hash of the pay to the simplex state, and that's it. And then B will just add the same pay hash to C and C to D. So these are very simple operations. And note that here, when relaying a payment, B and C simply relay, just add the pay hash into the pending pay list. And they never need to look at what the conditions are, and they don't need to perform any on-chain view for security check, just a pure off-chain communication. And say when say A and D play some games or like for whatever reason, if the conditions are met, and A will make the conditional payment to unconditioned by confirm the payment. So A will ask B to sign a new state, remove the pay hash from the pending pay list, and X amount to the unconditional transfer amount. And then B and C will do same to its next hop. Here is similar to the previous steps. By relaying this information, B and C still, they don't need to look at anything into the payment. They don't need to do any on-chain view for security check. Also very fast and cost efficient. See, if D, if the conditions are not met, so then means the payment will not happen. In the corrupted case, D will reject the payment. Will ask C to co-sign a new state and simply remove the pay hash from the pending pay list and not change the unconditional transfer. And C and B will do the same to its upstream hops. Again, no condition check, no on-chain view. So what if D wants to resolve the payment? What if the conditions are met, but D didn't receive the payment, either because A didn't send it or because B and C didn't relay? So in this case, D will resolve the payment on-chain. For this, we have the separate contract called Pay Registry, which is global shared by everyone, by all pays. What is essentially is the hash map. The key is the hash of the pay. As I said, each pay is unique. So by simply looking to the hash of the pay, you can get the payment result. So D will resolve this payment on-chain and write the pay result into the pay registry. This is one on-chain transaction. And after this, D can ask C to to confirm the payment because the payment is already written on the pay registry. C can safely pay D in advance before receive the confirmed payment from B because it is already finalized. And C and B will do the same with its upstream. And in either of the case, if the upstream does not cooperate, the node can always decide to settle or close the channel. And during the payment channel settle process, the channel contract will go over the pending pay list and find out that this pay has already been resolved in the pay registry, so that the fund is safe. The payment will go to the right people. And here again, you can see that B and C, in case of dispute, B and C still simply relay. They don't need to do any on-chain transaction, but now they need to perform on-chain view functions to make sure that the pay is already resolved in the pay registry. And since each pay has a deadline, so if there's the conditional pay was set up, but it was not resolved before the deadline, and all nodes can safely remove the payment before from their state proof, because this pay will never happen according to the contract. In this case, none of the nodes needs to perform any on-chain transaction. Here, I want to stress that the main takeaway point is that for the Boolean payments, which is the most common payments in our view, so the relay nodes never ever needs to perform any pay-related on-chain transaction in any case. In this way, we can run a very reliable, robust, and high-performance relay node that can support tens or hundreds of thousands of users and very high volume transactions concurrently. Okay, so that was the generic payment channel. And here now I want to talk about our design for the applications that that people can use. So our Celer app can, if you only want the applications to work with our payment channel, you actually only need to support 2 simple API based on the type of the results, the condition you want to provide. So first is like either it's if the condition is finalized and then get a result. Either it's a Boolean result or it's a numeric result to return the actual amount you should pay. And here it's just a recap of our condition and the transfer function. Yeah, so it is pretty simple, and so you can just add this API into any existing contracts to work with Celer Pay, and the Celer Pay, the payment channel, do not care anything about how the internal condition logic is implemented. But we also have our own application, a higher level application development platform we call Celer app. It's a mobile platform, and to allow users to quickly develop mobile games on blockchain. And in order for the apps to work with our Celer app, with our Celer X platform, we require some more app-related channel logic. There are mainly 2 types of app. One is a multi-session app. It is mainly used for the apps that can be deployed by the developer once and then shared by all the players repeatedly. So, and there's no contract deployment needed when a player wants to bring the game to on-chain. And we also provide a single session app template, which is mostly used as a one-time virtual contract without initial deployment. But of course, if the player wants to dispute, it needs to first deploy the contract. And the app, say game developers, they only need to focus on the app logic. So the most common logics are implemented within our backend and our templates. So now let's put it together to see how the end-to-end flow works. See now, A and C are connected to our relay node service B. They have a payment channel already open, and A and C want to play a game. So they just need to communicate with each other through whatever communication channel they have to set up the game, to set up the off-chain payment channel, agree on the nonce or whatever. And then they can just send pay to each other, 2 conditional pay to each other. So they share the same type, share the same condition address. The only difference is their condition arguments are different, A wins or C wins. And B will relay the payments. And A and C will exchange to confirm that they have received the payments receipts. And then they can safely, through off-chain communication, to co-sign their updated off-chain game states to do all the off-chain game playing. And C, finally, if C wins and if A is cooperative, A will just first confirm the payments to C and reject the payments from C. And through the whole process, there are 0 on-chain transaction. But see if C wins, but is not cooperative, then of course their on-chain dispute is required. So now C needs to first on-chain settle the game state by submitting the off-chain game state to the game contract. If the contract is a virtual contract, it needs to first deploy the contract, and then resolve the payment, saying that, okay, to finalize the payment in the pay registry. And after that, C can safely require the upstream relay nodes to confirm the payment because the pay is already finalized. And for the payment from C to A, people can just wait till timeout. So in all this case, B just simply do all the relay nodes to facilitate the process. Okay, to recap, so our main goal is to design like a very robust, high performance off-chain services that can always online, that can have minimal cost, that can be shared by everyone. So so there are different trade-offs we have, and the main design choices we made is to decouple payment channels and app channels, and use protobuf that I didn't go into detail today, but we have the open source protobuf decoder implemented, and people are welcome to try out. And 12 our ongoing work, the one is seamless, low cost, zero downtime smart contract upgrade. Because yeah, we can always find out, okay, we want to support this feature and we want to make it better, but we are trying to have a protocol that can make sure that the off-chain payment channel and off-chain game channel can still seamlessly continue running while people collaborate upgrade the channel contract to a newer version. And we are also implementing the state guarding functionalities to guard the state, saying that if one peer is offline, it can ask others to guard the state for it. Okay, that's it. Thanks.
How does this work?
I don't know how it works either, but I can try.
Oh, yeah, keyboard.
Yeah. Boom. I don't want to click on something I'm not supposed to click on. Oh, that's it?
Perfect.
Fuck yeah. Literally just clicked a random tab and it was it.
So how do I make
Click sign in.
sign in? Okay.
This is the last talk for today.
And then click present.
Perfect. And then just click, right? Or you can use.
Keyboard.
Okay, great. Yeah, hi everyone. My name is Alex. I'm gonna make a closing keynote, and I'm gonna make it short for you so that everybody can go to dinner or lunch fast. I'm from Matter Labs. Matter Labs is a small group of researchers, developers who work on bringing academic stuff around zero knowledge to practical implementations. So we look what's interesting there, and we try to make it something which can be actually used for real purposes. So my talk is going to be about ZK Rollup. How many of you are familiar with ZK Rollup? So everybody knows it practically. I gave many talks about what Rollup is, so I'm just going to focus on the current state of affairs and current challenges. Yeah, so I'm going to skip this part mostly. So it's a scaling technology. I'm just going to emphasize one thing. Rollup is very similar to Plasma. It allows state transitions being secured by zero knowledge proofs instead of solve the data availability problem in a very different way from anything else. So we'll focus on this later in the talk. So it can be done with snarks and starks equally. Starks are a little hard for now because the proof sizes are large and we need to solve data availability, so we need to spare space in the Ethereum block in the call data for that, but theoretically it's possible also with Starks. But we're doing it now with Snarks. So here's like the account model, Merkle trees, blocks. It's state transition. You can look up the other presentations if you're interested. So what are the promises of Rollup? It solves quite a lot of problems. It can allow pretty high transaction throughput, and it's going to be decentralized transactions at roughly the same security level as layer 1. So it's almost as secure as layer 1, and additional security assumptions which we add are purely mathematical. They are just based on cryptography. There might be some stronger or weaker cryptographic assumptions about this, but they are not subject to any manipulation by intelligent agents. And if there is some broken cryptography in elliptic curves or in other assumptions, we'll probably see signs that it's broken earlier than they can actually get exploited. So this is very interesting. And it's for operators, unlike proof of stake, they don't have exposure of the private keys on online machines. So they don't bear security risks in this regard. And the usability is actually much better than alternatives which we have now. For example, in Plasma, we have a liveness assumption. Users have to appear online from time to time to check whether transactions by the operators were fraudulent or not, and then respond with challenges. And this introduces delay lockout times where I have to wait maybe 1 week or at least several days until I can use my money or withdraw them from the sidechain, because in this period somebody else might challenge me. So with rollup, with ZK-based state transitions, we don't have this. The finality is fast. As soon as we have proven the state transition, it's final, and you can we submit it to the smart contract on the main chain. Proof is verified, and then it's final. You can immediately take money and use it and withdraw, for example. And it's also capital efficient. You don't need anything like what we've seen in state channels, any additional capital parked, which cannot be used. So quite cool. I forgot censorship resistance, because we publish all the data via Ethereum. We have data availability guarantees by Ethereum itself, and this means we can have multiple decentralized operators who produce blocks in turns, or we can govern it some other way. So we can actually create some constructs which do not allow centralized censorship of transactions. All quite cool, but let's see what we can actually have, what's possible right now, and what are the challenges. First of all, throughput is on Ethereum is currently hardly limited by 500 transactions per second, and this is already very optimistic. It's like just one token, or like Ether itself, being transacted with up to 24 million potential users. And the reason for this is that we put all the data, for every transaction, we put some small part of data on chain. We don't use storage, but we just broadcast it via call data. For example, if we use tokens and we have 24 million users, then this is roughly the amount of data which we need to publish per transaction. So we could not do this with Plasma, for example, because for Plasma, we would have to also publish the signatures, which are much bigger, to be able to verify them. This is the limit, because we have block size limit in terms of gas. There is a mitigation in progress, which Ellie mentioned yesterday, EAP 2028, which hopefully will reduce the call data gas cost significantly. I hope maybe by a factor of 10 or maybe even more, which will immediately increase the throughput capacity of current rollup by the same factor. So if it's increased by a factor of 10, then we will be able to handle 5,000 transactions. So this is roughly the situation with throughput. Time to finality. So while the time to finality with rollup is much lower than with Plasma state channels, it's still not ideal. So with the tests which we conducted at the moment, we can achieve block confirmations within 5 minutes at roughly 0.05 cent per transaction. So what's important here is that finality time is an economic target. We can lower it arbitrarily. Like we can, because all the computations which we do are highly parallelized, we can just increase number of processing power by a large degree, and we can lower it down to like 1 minute or half a minute or 10 seconds. But the cost per transaction will increase, at least if the number of transactions also doesn't increase by this number. So Yeah, so it's a trade-off. So the more we can push down the cost of prover, the cheaper it can be at a reasonable number of transactions. And this is what we're working on. So I'm actually excited to announce that we just released the GPU Snark Prover. It's available on our GitHub. It's already costs 1/3 of time on an average machine to produce Snark proof as compared to doing the same thing on CPUs. In economic terms, though, the current GPU prover is roughly equivalent to the cost on CPU. So if we use, let's say, some cluster of AWS machines with GPUs, it's not going to give us significant benefit yet, but it's the code is not yet highly optimized. It's just the first GPU prover which can be actually used to construct complete Snark proofs, and not just part of it. Some parts of it are already faster or already more economically efficient than CPUs. Others are not there yet, but we want to optimize them, and we want to invite others to also collaborate on this. Trusted setup. So unfortunately, all this efficiency which we have with Snarks, as opposed to Starks, for example, are coming from the fact that we need to do significant pre-computations, which include also something we call trusted setup. This is a ceremony where multiple participants donate their entropy, and then they promise to delete some data which they use to generate this their computations, which is referred to as toxic waste. And the properties of existing multi-party ceremony computations are such that if at least one participant is honest, nobody can make fake proofs. But if all of them collude together, they could then break the security of the system. And unfortunately, the most efficient proof system which we have right now which is Groth 16, also requires a circuit-specific trusted setups. So we need to do it for every application, for every upgrade of the application, which is really uncool. There are efforts to change this, and such as Sonic, and recently we had a newly published Aurora Light paper, which have a universal and updatable trusted setup. So we can do, or CRS, a common reference string, which is the bytecode of the setup, which means we can reuse the same trusted setup for multiple circuits up to a certain size, which would practically solve the trusted setup problem, because we can just have a lot of people participate and add their contributions over and over and over a longer period of time, and we have multiple, like thousands of people and organizations participating. Unfortunately, these proof systems are not yet as efficient as Groth 16, but we'll see what happens there. So then finally, we have, in order to implement something with Snarks, we need different approaches. We cannot just take normal programs written in Solidity or other languages and convert them into something for which we can generate the zero-knowledge proofs. We need to design these programs specifically. So we have some languages or frameworks with some domain-specific languages which support writing Snark proofs. Most famous ones are probably LibSnark, followed by Bellman. There are some other newer ones. Some of them are also based on LibSnark. I'm not sure Circom. I think Circom is completely in JavaScript. I don't remember. But only LibSnark and Bellman are actually very efficient at the moment. So you can use others for some smaller programs. But if you want to write something complicated and heavy, then you have to refer to Bellman or LibSnark, and they're both not optimal yet. So with, for example, C++ in general is a very difficult language where you can have a statement like, if I greater 0, then do something, and it will work like even if the I is negative. So there are some edge cases. C++ is pretty old and was not designed for being secure. Rust is better in this regard, but the way programs are constructed is currently not very readable. It's quite hard to work with. So we need some improvements here, but it's possible to do. So it's quite efficient already. So it's working. So this is roughly the state. Infrastructure. So we recently run why infrastructure is important? Because the proofs are quite heavy, and if we want to reach the finality targets of like 5 minutes, we need to, for larger blocks, we need to run computations on a lot of machines. So we had a recent test running on DigitalOcean with proofs being submitted on the mainnet, actually, to test the entire integration. And we used all the available capacity of DigitalOcean's largest server type. So if we went for different, we just wanted to have the same server type for across all provers so that we can benchmark it easier. But we had like 100 machines there, and it's quite a challenge. We had to provision them from different data centers. So it's working, but we still need to make a lot of improvements, and hopefully the prover efficiency will increase, and we will need less of these machines, or maybe we can distribute it across users with GPUs, so who knows. So this is roughly the state, but I want to give you the future outlook. So as you can see, we're very, very early with rollups. It's what we currently can do. Probably this year, we'll be able to deploy something very simple like ERC20 token transfers, maybe DEX order settlements, maybe some variation of state channel updates or state channel finalization. But at the moment, we need some improvements. But I want to make a few predictions to sound more optimistic. Number one, data availability will gradually become cheaper. So we'll start with EAP 2028, hopefully, and then we'll progress to sharding, where Ethereum's philosophy for ETH 2.0 is actually to be the data availability layer and consensus layer, and everything else built on top of it will be layer 2, which will inevitably make the the cost of data also with sharding cheaper. So we will be able to increase the throughput significantly by this. Second, the prover efficiency is going to increase. So there's going to be a combination of different factors, such as the improving of efficiency of the software itself, improving of GPU provers, but also this is the different part. So yeah, we think that we will see improvements in the pairing based proof systems overall significantly over the course of a few coming years. So we see there's something like Cambrian explosion coming with these proof systems, which are probably going to become more efficient, probably going to be based either on universal trusted setup or even on some transparent trusted setup, which just generates some large pre-computation, which makes the proof generation then efficient. So we're very excited to follow the space, and I encourage you also to follow it. We're going to see some strong improvements, maybe even by the end of year. Oops. Now, yeah, the prover efficiency, regardless of which proof system we use, is also going to increase. And not only based on optimizations of the software, but also on the Moore's law itself. So if the Moore's law continues for the next 5 years, we'll already, just based on this, we'll be able to reach the finality times of just a few seconds, so maybe half a minute. But also with other things like GPUs and some optimizations and maybe more like specific hardware, we're gonna reach the finality or proof generation times below the times of Ethereum block. So Ethereum block generation time will be the bottleneck, not the prover. And finally, we expect, because of all of this and increased interest to the subject, we expect that the quality of the DSLs, profilers, tools, developer frameworks is going to increase significantly, such that we will be able to build quite some amazing stuff. I think it's going to be a game changer in the years to come. We will have arbitrarily smart contracts, and these smart contracts will also have privacy properties. So we'll be able to do what we discussed yesterday with in the Uniswap workshop, for example, a Uniswap on ZK rollup, with dark pools, with users building their own smart contracts, which are only visible to the people they authorize, and so on. This will take some time. We're not there yet. It will take like significant time because we need to solve all these problems, but it's very interesting and it's very promising. So I want you to encourage to look at the topics which we have now, which are open and require research. I'm happy to discuss it personally with everybody after the workshop. Just look at this, look at the new proof systems, look at prover efficiency optimizations. We need optimizations of the primitives which we use inside the circuits, such as hash functions. There are some new hash functions appearing, like Poseidon and Hades. Some snark-friendly or Stark-friendly vector accumulators as alternative to Merkle trees. We will need people who want to work on the DSLs and make the developer experience better. And we'll also, what's very important is also that these DSLs support formal verifications. They will convert to R1CS or maybe to some other language which can be efficiently proven in this zero-knowledge proof systems. But we'll need the same thing as we need for Solidity in Ethereum, that we have specs and then somebody can prove that the specs are correctly translated into zero-knowledge proofs and that the models and the verification keys correspond to these inputs and so on. So these are the areas which are like super early, and I think this is the most interesting stuff in blockchain. You can work this and create a lot of contributions. So I just want to encourage you to look into this. And that's it on my side. Thank you very much. I'm happy to answer your questions.
We've got a question in from Twitter.
Yep.
It says, when Stark ASIC?
When Stark ASIC? Okay, well, Eli just left, so it would obviously be addressing him, but like soon.
Okay, I'll tweet back.
Yes.
The cost per transaction you mentioned, was that for prover time or gas or both?
That's for prover. The gas cost will be roughly like 2,000 gas per transaction. So we always have the gas part on top of the prover part, which is going to be the bigger bottleneck. The prover from now on is only going down. It's really hard to make the gas part lower. It's already like super optimized down to like we use compression of the amounts and fees with exponent packing. So like it's compressed down to bytes, which we can like. It's really hard to go below. Yes.
Where do you see the greatest synergies between DK rollups and other?
This is a great question because rollup is actually very similar to Plasma, and we can perfectly see the interoperability between rollup and Plasmas. Rollup is fundamentally less scalable than Plasma, so because we have to put all the data on chain. So I think rollups and Plasmas can be used for different purposes. Rollup is something which is like super high security. Maybe for like currently you have to wait like 5 minutes. It's not like state channels where you get immediate confirmation, which is probabilistic. You have to wait this 5 minutes until you have your finality. So if you're doing some trading, maybe it's okay, like on high volume, high value assets. But if you're playing some games or doing something like I don't know, like some other use cases, maybe you want to use Plasma, so it would be ideal to have some bridges to connect them. Maybe we can use the predicate framework and these interfaces to just to be able to move funds from Plasma to rollup and back and interoperate.
I think in financial services, sort of like DBP, I can see that that would be really good, so that you can avoid stupid things like private channels for payments, which are just pain in the ass.
Absolutely. So yeah,
you can't move assets between private channels. So whether it's Quorum or Pantheon with Orion, once you create the asset in the private channel, to move it out becomes just a pain.
Yeah. Sure.
So why do you need to store everything on chain? Is it just to solve data availability, or is there some other?
So we don't store anything on chain.
So what?
We only make data available through Ethereum by abusing call data. So we pack the data and put it on transaction, and then everybody who has access to Ethereum can just get the next block, extract this part and collect the data. So what it and we only post the delta of the state. Like we only post information which allows you to reconstruct the transition, what changed. So like what you do is you can take an archive node and run all the transaction from the beginning and reconstruct the state. And now you know exactly what the latest state is, and it corresponds to the Merkle root hash, which is recorded on a smart contract. And now you can prove that you own something in the latest state without asking operators to do anything for you. So you can always exit your funds. You can always withdraw all your assets from the rollup chain. Like you don't have to challenge anybody. You don't have to play like the mass exit problem does not exist for rollup. And this is actually the crucial part. This also allows us to have account-based model and not UTXO model, which makes things much simpler for like number of applications. Yep, so I guess that's it. Thank you very much.